In this lecture, we will be discussing kernel methods for pattern recognition and machine learning. The current machinery of machine learning techniques so far includes the linear models, which we have discussed in the context of regression classification, and neural networks. And in all of these cases, we had some training set comprising of an input X and then the corresponding target outcome T, and we were training a function Y, which was supposed to estimate for a new input vector X and the target outcome. And this is based on trained parameters. We were training the parameters W, the weights, which formed then the linear combination of our feature vectors, and then led to the desired functional outcome, either telling us what is the estimated value for in the case of regression, or the class for the task of classification. What happened there was that the parameters W were learned during this process from the input data, and then the input data was discarded. So we simply didn't use the input data later on during the inference process, because it's the learning captured the function in the weights W. And in the neural networks, we have the same approach. We do not really use the data set, the training data, at the inference stage. We are only using it during the training. However, there are other methods which are using this training set for the purposes of regression or classification. So we will be categorizing these techniques as memory-based methods, where we had already back in the chapter 2, we discussed these various approaches, which were based either on the kernel density estimators, and there in that context we were mentioning the Parson window, or then the Parson probability density model, which was then based on some kind of a rectangular neighborhood from our input point. And then there were also the nearest neighbor methods mentioned that do not discard the training data. They basically utilize the training data in order to give the estimation of a particular value in a particular point in space. And in that regard, they also correspond to reconstruction methods in signal processing, where a certain kernel is giving a particular weight to neighboring samples, which then will be used in reconstructing a particular value at a given point in space. Generally, these techniques are fast in training, so sometimes they do not require any training, sometimes some form of training or pre-processing is necessary, but they take longer time to make predictions, because sometimes we need to go through all of the input data in order to make the prediction of the value at a particular position. Models which we were discussing, which train a certain set of weights, and then they discard the actual training data, can be recast into a so-called dual representation. Let's have a look how this can be achieved on the couple of next slides. These predictions can be based on a linear combination of a kernel function evaluated on the training data points. And this relates very tightly to the reconstruction task in signal processing. The in the context of machine learning, these models with nonlinear feature space mapping, phi, are need to satisfy the condition of a valid kernel, that the kernel can be constructed by some dot product of a feature feature points between our point which we are trying to estimate the value of x and some other points x prime in from the training set. So the kernel needs to satisfy the condition that we can formulate such a feature mapping phi, which then will form this kind of dot product. The simplest linear kernel would be simply just a dot product of the input vector x at the new location and some neighborhood x prime, which would clearly satisfy this condition because we have the phi is just an identity function. Earlier, we have discussed in the Bayesian linear regression case in the chapter 3 a so-called equivalent kernel, and there we which was the equivalent kernel was equal to a beta phi x transpose Sn phi x prime, and that relates to the various quantities and structures we have defined in that case. So we had a posterior probability distribution there, where we defined a normal distribution by some mean Mn and some variance covariance matrix Sn, and we also defined a noise variance beta in this case, and we had some feature mapping function phi, which is transforming our input vector into the feature space. And with this formulation, we can see here that except of having here a matrix and the scalar term precision beta, we in fact are having here a the feature vector, so which is in some sense forming a dot product, but there is this this matrix, the covariance matrix Sn. The covariance matrix Sn we calculated as an alpha times the identity matrix. So this alpha was this prior which was defining as the spread of the weights W from 0, and then we had the beta multiplied by the design matrix transpose times the design matrix, and this was forming us the precision matrix, and the inverse of it would be the covariance matrix. So we already were using this equivalent kernel before, and it could have been used for defining a value x at a particular location of the and from the training set, and represented by this x prime. So here the value of the regression y was of x given the mean value at the posterior mean was equal to the sum of kernel values where we evaluated this function, and here instead of x prime we would have xn from the training set, and the output of the kernel was used for forming the linear combination of the values Tn. So we can say that the y was created as a linear combination of the Tn values weighted by the kernel, and we made this sum over all of our sample points. So in this way, we were able to obtain the same mean, the same value of output y as we would be obtaining through the parametric model, where we would be looking for the mean value in this Bayesian linear regression case. So we already have seen a glimpse of this, and we will be using a similar, we will be devising a similar form of in the next slides, coming from not the Bayesian linear regression, but from a regularized sum of square differences, which are tightly related. So just for recapitulation, in our approach when we were training weights, we had this error function. In case of regularized sum of square error, we would be having the two terms. One is the data term error, and one is the error coming from the regularizer. The regularizer is performing the squares of the weights, and we want the weights to be minimal, and this is governed the contribution by the parameter lambda. And then we have our error term for the data, where we are measuring whether this linear combination of the features weighted by the weights is close enough to the target outcome for the training set pairs xn and tn. So with this error function, will be then measuring this error for the entire training set, therefore this sum here. And we used the approach to obtain the weight vector by for the closed form by setting the derivative of the error term with respect to weights to 0, which will mean that when is this function obtaining is minimal value. So we want to minimize this error term overall, and this is by for convex problems can be found by the minimal point, and that can be found by the derivatives. So from that we obtained the formula, which was so we performed the derivative, where here deriving this term will lead to 2 times the outer term is first derived, and then the inner term, the outer term, the derivative with respect to weights will lead that this 2 becomes from the exponent and multiplier is cancelled out with this 1/2, and then the derivative here will lead to 1 phi xn term, which means that the derivative of this first part is equal to this sum, where this offset of the estimation from the known true value is multiplied by this feature of the corresponding input point in the feature transformed into the feature space. Now then we also performed the derivative of this term, where we had the result was then the lambda w, and that we now, as it was equal to 0, the derivative, we put it on the other side, where we were then having it in the value as minus lambda w, and then we divided both sides by this reciprocal of minus lambda, and we ended up in this term. So the weights can be expressed as being equal to this term, when we can see that the weights are actually represented on both sides. Nevertheless, we can coin that that we have a certain value, scalar value an for each training point. We have this an scalar, which is actually equal to the dot product, or this linear combination, minus Tn, and then scaled by the 1 divided by lambda minus. So we have it here, the an. So we just reformulate this sum, and we can also, instead of this sum formulation, can have it in a matrix vector multiplication form, where we have the design matrix transposed times the this newly defined vector A, measuring this deviation of the estimated value from the true target values scaled by this term. So that is the newly reformulated form. So we are replacing the W with this design matrix times transpose times A. Now let's have a look once again what this design matrix is. So the design matrix, capital Phi, is actually the feature vectors of our input points, where each input point is forming one row in this design matrix, and it is a transposed feature vector. So this feature vector is having individual components, which will be these feature functions, these feature mappings, which are different for each component of this feature vector. And in this first row, we will have these individual feature vector transformations of our input point x1, which is an input vector. And then we will have it for the x2 up to xn for all the input points. So once again, we can see that in the rows we will have the input data points, and in the columns we will have the corresponding components of this feature vector map. So but this is just a recapitulation. The key point from this is that we are now replacing the formulation of the weight W by this design matrix transpose times this newly defined quantity A, which also contains admittedly the W term here, because it's composed by this formulation scaled by this minus 1 divided by lambda. Now, after we perform this substitution, we can formulate our squared term, which we had before, from the error term, as by replacing this vector of weights W with the newly defined quantity A and the design matrix Phi transpose. So we have performed it here. We can see that in this case here the W is transposed, so we transpose this, and this is A transpose Phi, and then we have the rest in the same way. And this can be reformulated in a vector form into the design matrix times design matrix transpose A minus T and the whole term squared. So therefore we have here that is equal to this formulation here, and that can be multiplied, that can be constructing us this term of the error, which we will see here, and we will go through it step by step. So let's see how these terms multiply. So imagine we take the first term and we transpose it. So what will be the transpose? The transpose will lead to having the A being in the front, so we reverse the order and we reverse which term is transposed and which one is not transposed, and then we multiply it with this first term here, which leads to the first term, which is the A transpose phi, phi transpose phi, phi transpose A. So this is this squared term, and then we have the linear term associated by mixing this first term and the second term, and we have it twice, which is here, and then we have the last term, which is just T transpose T, which is this term here. And we can see that in this error term expressed now through A not weights, is we have 1/2 here because we had this 1/2 in the front of the data error term, and then this 1/2 is not here because this term we have twice, and here we have again this 1/2. And then naturally for our weight term for the regularization, we have here the W transpose times W, which is replaced again by the A transpose phi, phi transpose A. And now this relatively complex formulation, but we understand it how we came to it by replacing the W by the phi transpose A, according to the previous slide. We can also replace the phi transpose by the so-called Gram matrix K, which is in fact the phi times phi transpose. And this Gram matrix K has the entries N, M in our matrix, which are basically composed simply by the dot product between two feature points, feature point xn and feature point xm. And that is in fact the kernel X with 2 points, xn and xm. So we can see that this Gram matrix, now we see how we are coming from the parametric weight-based representation into a representation based on kernels. So while we admittedly in the case of the A still have the weights somehow present here, at this point this Gram matrix is not representing any weights because it is based simply on the design matrix and its transpose, and we can see that the individual entries are simply the dot products of the phi feature map vector from 2 points, and that basically is formulating the formula for our kernel K. So we can also say that our Gram matrix in each entry has an evaluation of the kernel values of 2 points xn and xm for the n and mth entry in this Gram matrix. Both of these are coming from the training set, of course. So we can observe that we have several times this gram matrix in our formulation, so we can replace the error term JA with the instead of having the design matrix, having there the gram matrix mentioned explicitly, which is calculated from this based on these kernels, and we see that this gram matrix is appearing here twice because it's here twice, then here once, and then here in the regularizer term it is also once. Now, if we set this formulation to 0, so we want to again minimize this error, but now not with respect to weights, but with respect to A, as we have now expressed our error term with the A vector, we can perform the derivative of this term and set it to 0. So if we perform derivative of this first term, and then we can divide it into partial derivative of these individual terms, as we can see here. So this is one a term, another term is the second one, here is the third one, and this one is left out because it doesn't depend on A, this square of t. And therefore, our outcome will be that, so from this term, we will have the result kka is the partial derivative of this term, and then the minus kt is the partial derivative with respect to A of this term, and then the lambda ka is the partial derivative of the regularizer term. And therefore, what we can express here is that the k, so we put the kt on the other side and then express the rest terms by taking out 1k, and then because we have here it twice, here it's once, so we end up with sorry, here once, so we end up in the inner term like ka plus lambda a coming from these two terms times k is equal to kt, and if we remove the k from the left from both sides, we end up, or multiplied with its inverse, we end up in the formulation where the k plus lambda I times the a is equal to t. And from here, we can formulate that the vector A is equal to k plus lambda in. So this is simply a diagonal matrix with the lambda in for each entry in the diagonal, and this matrix inverse times t. So we see that now our A is becoming the linear combination of t entries multiplied by this matrix here. And here we can see that in itself it no longer depends on the weights W in this particular formulation. Now finally, we can, after obtaining the formula for the vector A, we can substitute the weight vector into the linear regression model, where we substitute it with the A transpose phi design matrix times the usual feature vector for our point x, and then we can also reformulate this as the dot product of where we reverse the two terms, and then the phi times phi design matrix with the phi feature map of of the point x is representing us the kernel, but this is no longer a just single kernel scalar outcome, but this is a kernel vector. So we essentially calculate the dot product of the phi x with all entries in the training set, phi x here, x1, phi x2, phi x3, and so on until phi xn is dot product with the phi x, and that forms this vector kx here. So again, it's this vector kx coming from this term will become the dot product of phi x with phi x1 to phi xn in each it will as a column vector. So the first entry will be the dot product phi x times phi x1. The second will be phi x times phi x2, and so on, to form this vector kx. And the second term here is already known, what we devised from before. It's our variable a, which is now replaced by its formulation by the gram matrix, this diagonal matrix with the regularizer lambda, and the whole inverse times our target vector. So I also put here the representation of this term here, where we can see that the design matrix times the feature vector is simply this representation of the vector, where we have this dot product between the phi x1 and times phi x up to the phi xn, and that is the kxnx, or just abbreviated as kx here. So now we understand how we can create from a parametric weight-based representation of our for our regression function y a kernel-based representation, which is not based on the weights at all, and it is only based on the input data points, and needs to be calculated for the outcome for y needs to be calculated by evaluating the kernel for all the dot product with all the phi's from the training set with our new vector x. So these two representations are called dual because one can be expressed by means of the other, as we still have the representation that the W is equal to the phi design matrix times transpose A, and this formula will allow us to transform between the two representations, the weight-based representation and the kernel-based representation. Now, that's also a way how we can construct kernels in machine learning. Generally, the idea could be that the kernel can be defined through feature space mapping phi. For example, for the one-dimensional input space x, so here we do not have it as a vector, but we have it as a scalar. In this case, the kx x prime is equal to the dot product between their feature space mappings of x and x prime, phi x transpose, and the dot product with phi x prime, and that is equal to, because these are itself vectors of mappings, is equal to the multiplication of the individual feature functions phi I, and then sum of them. So it will be, at the end, the outcome will be a scalar value of this kernel. So, but this is not the only way how we can construct a kernel, and now we will be spending some time discussing how these kernels can be possibly constructed and what conditions do they need to meet. Essentially, there are two conditions. Or the condition is that any kernel we use in the kernel methods for pattern recognition and machine learning need to be representable by some feature mapping vector and the dot product between the two input space vectors. So but other than that, we can construct various kernel functions for various purposes, as we will see in the next. So, for example, if we have this term here, k x set, so two input points, let's say, from the input space, are having the kernel is equal to the x transpose z and the square of it. The question is this a valid kernel? So in other words, is it mappable to a dot product of these two feature map vectors based of their input points x and z? So let's have a look what this really is. So if we perform the dot product here, that is equal to x1 times z1 plus x2 times z2 and the whole thing squared. And now we evaluate this squared term. So we have x1 squared z1 squared plus 2x1 z1 x2 z2 plus x2 squared z2 squared. And these can be reformulated into a multiplication of two vectors, and that could be like the vector can be consisting of so this vector consists only of some functions of the input point x. So here is the first entry in these three components, x1 squared. The second entry is square root of 2 x1 x2, and the third entry is x2 squared. And in the second part, we have the z1 squared, and the second component will be square root of 2 z1 z2, and the third term will be z2 squared. So and that is basically, we can define these two as being our feature mapping vector, and that one with having three components. And if we perform the dot product with this feature mapping vector of functions, then we will obtain this result. So that means that we will obtain this result and we will obtain this result. That means that the K is a valid kernel. Another condition is that the Gram matrix must have these entries, as we discussed before, and it needs to be positive semi-definite. So that means that if the Gram matrix is multiplied with an vector x t, and then with the matrix and then x, so x transpose k x must be the outcome of this calculation must be either positive value or it must be 0. So it doesn't mean that it needs to have positive entries as in the matrix, as might be a naive interpretation. So now we have now we can see that we have created an arbitrarily based function here, and when we realized whether it can be actually a valid kernel, and the answer is yes, it can be a valid kernel because we found the corresponding feature map vector. So we can construct kernels basically in two ways. Either we define the kernel through its feature maps, and which will then define the dot product of these two feature mappings between two input points, or we define the kernel entries directly. And in the direct construction of kernels, we either need to prove that we have the kernel is a valid kernel by creating the corresponding feature mapping functions, or we do not need to create these feature mapping functions, but we need to secure that that's a sufficient condition that the gram matrix is a positive semi-definite matrix. So in these images, we can see how the kernels have been constructed based on different basis functions. In the left image, we see on top, we see various polynomial degrees, and which will be then used for this feature map. So the first entry in the feature map will be a linear term x. The second feature function will be this quadratic one. Then the third one will be cubic, etc. So we have a polynomial degree feature mapping, and that can be represented in the dual representation by this following kernel, where it shows that given a point x, what will be the kernel value for point x prime, which will be at some value. So if the x will be at the value 0, if the x prime will be on this interval, what will be the corresponding values associated with this kernel function? Now we can see a very similar plot with these Gaussian basis functions, with the radial basis functions, where we can see various Gaussians as the basis functions, and which have the same variance, but have a different mean. So the mean is different, moving from between these interval -1, 1. And the corresponding kernel can be seen here, and exactly it's in the same way as the other kernel previously from the polynomial basis functions. We can see that the kernel looks slightly different, but essentially has the same kind of a structure. The same holds for sigmoidal basis functions, where we can see the sigmoidal basis functions here, and they have the same profile. Again, only the shift is a slightly different parameter, and the polynomial basis functions based on sigmoid would also lead to a kernel which is characterized essentially in a way that if the x will be very nearby to the x prime will be very nearby to x, it will have a rather high value, and with the increasing distance, it will be a decreasing value in the absolute terms. So it will be also could be slightly negative, slightly positive, oscillating around the value 0. So these are the kernels which have been created based on the training set, which you can see admittedly here are relatively small values for this kernel values because it is associated with the sum of all kernels weighting our target output, and the sum over all the training set will therefore be used for calculating the y of x at a particular location. Once we have a certain set of kernels, we can actually construct other kernels by certain kernel preserving operations. So imagine that we have a smaller building blocks of kernels, and we can build a more complex kernels, like we have a kernel K1 here and K2, and we can see what type of kernels we can be built, which are valid kernels based on these. So here are these several in total 10 rules, which we can use for building more complex kernels. So for example, multiplication with a constant of a kernel yields a valid kernel. The second is if we multiply our kernel with a function, any function of x and x prime, that will still yield a valid kernel. If we have a kernel which a kernel K1 is an argument to a polynomial with non-negative coefficients, this will be a valid kernel. So polynomial of degree 2, polynomial of degree 3, this will be a valid kernel. And then if we have an exponential function with a kernel as an argument, this will be a valid kernel as well. And then we have, for example, sum of two kernels is a valid kernel. Again, multiplication of two kernels, the product of two kernels, is a valid kernel. Or if we have a perform certain mapping of our input x and x prime with some mapping phi, which is again like we can imagine like a feature map vector of a degree or in the dimension m, then if the K3 is a valid kernel in Rm, then this will be a valid kernel. Then if we have the positive semi-definite symmetric matrix A, then its multiplication with x transpose A and then times x prime will be yield a valid kernel. Then for the last two cases, imagine that we have an x is a vector which can be decomposed into two subvectors, like the first set of entries and the second set of entries. Then if we have a valid kernel Ka on the first set of entries and the valid vector valid kernel Kb on the second set of entries, their sum will be a valid kernel for the x. And the same holds for the product of these two subvectors and their associated kernels. So all these rules can be used for building gradually more complex kernels, and we will see it happening in the next cases. So far, we have discussed several rules of which kernels are being preserved being kernels under certain operations, and we also discussed some kernels why they are kernels, like for example a kernel of as a linear kernel, as we can see here, has been discussed, and also the linear kernel squared, whether this is a valid kernel. We have just seen it a couple of slides before. Now the question is whether the linear kernel plus a constant squared is a valid kernel. So we have several rules here, and one of the rules here is that so this term is a kernel, and in fact the constant is also a valid kernel. So now what we need to do now, we need to simply multiply out these squared terms so that we get individual components, individual terms, and we know that sum of individual of kernels is also a valid kernel. So if all of these elements of this sum is a valid kernel, then this whole term will be also a valid kernel. So what will be the outcome? So if we have like this term now squared without a constant, so this is like if we have this bracket twice and we multiply the first term with the first term, it will be like the previous case where we had this term squared, and that we know that it is a valid kernel. Then the second term will be like a 2c x transpose x prime, and that is like a linear kernel which is multiplied by a constant. And we know that that is also a valid kernel based on the rules which we have discussed on the previous slide. And the last term is c squared, which is a constant, and we know that constant is also a valid kernel. So therefore, this whole term will also be a valid kernel. So compared to the previous case where we had the dot product squared without this c, this was generating us a feature mapping phi where we had only quadratic terms, meaning that we had like from the x in one term, we had twice two components of x, maybe x1 squared or x1, x2, for example, in each of the terms. And this was mixed, as we have seen on the previous case, with the x prime. In that case, it was called z, and the z components and the x components were mixed together. But in all of these terms, we had a quadratic term that two components from each of these input vector were present in the term. Now, as we have the plus c here, then we will no longer have only the quadratic terms. Those will still be there, but in addition to that, we will have a linear term, as we have seen, and we will also have the constant term. So this will lead to a feature mapping with a constant, linear, and quadratic terms forming our feature mapping vector. Now, the next case is the kernel. The next candidate for a kernel would be the x transpose x prime and that powered by m. If m is 2, we already have shown that this is a valid kernel because we have found the corresponding feature mapping phi, but this is now for the general case of powered by m, whether this is a valid kernel. And we can see that if this is powered by 1, this is a valid kernel because this is a linear kernel. If it's powered by 0, this is a valid kernel because it's a constant, it's a 1. And if it's a m is 2, it's a valid kernel because we have already shown that. But for any other values of m higher than 2, we don't know. However, we do know that a product of two kernels is a valid kernel. So we can form a product of the linear kernel and the quadratic kernel, and that will be powered by 3 then. And therefore, that would be a valid kernel. And by this construction, we can construct the kernels of arbitrary power in the linear term. The question is, what is the result of such a kernel? And in the feature mapping vector, and in this case, as we do not have any constant added here, actually we will have all monomials of order m. So if this is powered by 3, then each of the components will be having some components of the x or x prime, actually 3 components of x and x prime in each of the terms. And so that contains all monomials of order m, but it will not contain any linear or quadratic or constant terms, because this constant is not there. However, we can imagine what this means. We have an example here, like if x and x prime are 2 images, then the kernel represents a particular weighted sum of all possible products of m pixels in the first image with the m pixels in the second image. This would be an example of applying machine learning in computer vision, for example, where we have 2 images. So imagine that we have one image, it's x, and its second input vector of rows of pixels, and all these rows of pixels will be forming one vector x, and also another image will form the x prime. And now we will be creating an all possible products of m pixels from the first image with m pixels from the second image with repetition of the pixels, a weighted sum of that. So each of these products of m pixels from one image and m pixels with another image will be additionally weighted by some multiplier. So this is how the application of such a kernel will look like. And then they will be summed up together, these products, into one scalar term eventually. And then we have the final case is the kernel of the x transpose x prime plus c powered by m. And the question is whether this is a valid kernel. So we have seen that all of the previous the x transpose x prime powered by m, this case is a valid kernel. So this is a valid kernel if we multiply this with powered by m, and all powers of this linear kernel will be a valid kernel, and all the other terms which are created, the constant, linear, and quadratic terms, will be simply a also valid kernels, because they will be simply based valid kernels according to the rules we have specified before. Either they are valid kernels from the perspective of being kernel which is a valid kernel multiplied with a constant, or it is a multiplication of 2 valid kernels, or it is a sum of valid kernels overall. So this rule-based construction will also apply here, which will show that also this kernel is a valid kernel. Now we will have a look at the next type of kernel, which is an Gaussian kernel, and we will explain why is it a kernel. So the Gaussian kernel, and here we see the Gaussian kernel function is claimed to be also a kernel. So let's see why is that a kernel. We see here, first of all, that this kernel is not having the normalizing term, but that is fine because we are not dealing here with probability distribution, but with a kernel function, which doesn't need to be normalized to 1 to begin with. So we have our exponential function, which we say it's a valid kernel. So let's have a look whether this is truly the case. We have here a case where we have a distance metric, essentially distance between one vector from the other vector squared, and this is divided by the 2 sigma squared constant, and it is a negative, and that is the argument of an exponential function. And now, in order to show that this is a valid kernel, we will simply multiply this this term here into individual components. So the individual components multiplied will be like x transpose x minus 2x transpose x prime plus x prime transpose x prime, and all divided by 2 sigma squared. So so far we don't see whether this is a valid kernel, but we see that we can take this exponent and use it for formulating a product of several exponential functions. So we have here, therefore, an exponential function x transpose x divided by 2 sigma squared. Then we have x transpose x prime divided by sigma squared, because we have twice that term. And then we have the x prime transpose x prime as an exponent for the divided by 2 sigma squared as the exponent of this third term within this product. Now we will, at this point, we can see that these three exponential functions have some exponents, and this central function, let's look at this central function first, where we have the x transpose x prime. So if we look at this argument itself, we will say that this is a valid kernel because it is a linear kernel. And we know that if this linear kernel is multiplied by a constant, is still a valid kernel. So everything what is inside this exponential function is a valid kernel. Then we also have a rule that exponential function of a valid kernel is a valid kernel. So therefore, we can say that this entire term is a valid kernel. Now, how about these parts? Are these valid kernels? Actually, they are not, and they actually also do not need to be, because we have a rule that if we have an f of x and multiplying a kernel, and then f of x prime multiplying it, then so multiplying a kernel from left by fx and from right by x prime, that's how it was formulated, is a valid kernel. And we can see here that here the f of x is simply e powered by x squared divided by a constant, and here e powered by x prime squared divided by the constant. So from that perspective, this must be a valid kernel. Finally, we have one more aspect here, that we know that this is a valid kernel. Now, what if we substitute that kernel, linear kernel, which is characterizing as in fact a distance between x and x prime squared, if we put in any other nonlinear kernel, so which is already shown that it's a kernel, but it's a nonlinear kernel. So we have a kernel k kappa x x prime, and we put it into the expression here. We will see that this will form us again 3 components, and thus like here, and it will form us a valid kernel. So from that we can also deduce that if we have a kernel kappa, which is expressing some other distance than a Euclidean distance, as it is here, it will still be a valid kernel. So we can have different distance metrics, except of the Euclidean metrics and in the exponential function, and it will still yield a valid kernel.
Next example about constructing a kernel is about constructing a kernel function that can be defined over diverse types of objects, not only over vectors. For example, such as graphs, sets, strings, or text documents. So that's why it will have a relevance in machine learning on top of these type of structures. So imagine that we have a fixed set S of objects, and there are two subsets, A1 and A2. And the kernel defining the similarity between A1 and A2 can be expressed by 2 powered by A1 and intersection with A2, so all the elements which they are sharing, and the absolute value here indicates the amount of elements, amount of subsets, which is then the exponent to the base of 2. So in case we have no common elements, so the intersection is empty set, then it will be powered by 0, and 2 powered by 0 will be 1. Now, if they have a lot of elements, let's say 5 elements in common, then this will be 2 powered by 5, and we can see that with increasing amount of shared elements, this number, the kernel function, will lead to a higher value. So the more elements between A1 and A2 are in common, the higher the number. Now, this is clearly some similarity function between two sets, but it's a question, is it actually a kernel? So in order to answer that, the question is, can we reformulate it into a product of two feature vectors where one feature mapping is associated with the argument A1 and the other feature mapping with the argument the subset A2. So, and we want to show that this is equal to the 2 powered by the number of elements in their intersection. So for that, we can define the following setup. Imagine that we have two 2D vectors, u and v, where u is 1, 0 and v is 1, 1, and we perform the so-called Kronecker product designed or defined by this symbol for defining a feature vector. So a Kronecker product of these two vectors will be defined in this way, where we are multiplying all the components of this product with of the vectors with themselves and forming a one long vector. So here we have the multiplication of the first component with the first component, the second vector, first with the second component, and so on. And from that we construct a new vector. So multiplying u, or not multiplying, performing this Kronecker product of u and v, we will lead to 1, 1, 0, 0. Why is that? Because this is the first component times first component is 1. First component times second component is still 1, because the v is 1, 1 and u is 1, 0. And then these two components will be 0. If we will have the product of the 2 times on u's, it will look like this: 1, 0, 0, 0, because only the first component with itself will be equal to 1. Then please note that this is not an commutative operation, and therefore we have a different result of the vector in the third case, where the v, the canonical product with u, is not equal to u canonical product with v. And finally, the canonical product of v with itself is 1, 1, 1, 1. So this is just an introduction of this new operator, which generates us a more dimensional vector out of smaller dimensional vectors. And now imagine that we define the feature mapping phi of A in a way that we have this Kronecker product over made over and over again in an iteration, where we go through our entire set S, and which is the set which contains both A1 and A2, and then for the argument we either perform the canonical product with V if the element of S which is currently considered belongs to A, and if it's, or we perform the canonical product with U if it doesn't belong to A. So as it is A is a subset of the capital S, some elements of the capital S, the A will include, some not. So, and based on that, we will either perform the canonical product with V or with U, leading to a very, very long vector describing the characteristics of its content as a vector. Now, imagine an example that we have just two components in S, S1 and S2. And then let's say that the A contains S1. So if the A contains S1, then we will have the V in the first case because it contains S1, and then that will be perform the canonical product with U in the second iteration for the S2, because A will not contain S2, so we will have V canonical product with U. And if we will have more elements, then there will be more of these canonical products. But let's just define it for these two. And let's say that so that's maybe A1. A1 only contains S1. And then we have A2, which, well, let's say, contains first 0 of these elements, so it will lead to a U canonical product with U 1, 0, 0, 0. So this vector, which is 1, 0, 1, 0, will be performing a dot product with 1, 0, 0, and that is equal to actually 1, because only the first elements will be multiplying 1, and then the rest will be equal to 0. So, and this is actually equal to the corresponds to this formula 2 powered by the intersection, as it is an empty set. 2 powered by 1, 2 powered by 0 is 1. So we will have the result 1. Now let's imagine we change the A2 that it actually contains both S1 and S2. In such a case, its canonical product will be 1, 1, 1, 1, because we performed the canonical product twice with the V, because for both iterations of elements in the set S, it was they were present in the A2, and therefore we chose to perform the canonical product with the V. And therefore, finally, we have the dot product between 1, 0, 1, 0 with 1, 1, 1, 1, and that is equal to 1 times 1 plus 1 times 1 is 2. So, and actually, so what is the the intersection between A1 and A2, well, one contains S1 and the other one contains S1 and S2, therefore the intersection is S1, 2 powered by 1 is 2, so which holds for this dot product here of these feature mappings. So we can see that this way how we defined the Kronecker product function here, we will be able to construct this feature mapping for which a dot product between the two subsets of S will create us will correspond to this similarity formula which we defined here above, and this means that as we are able to formulate it as a dot product of this feature mapping, that means that it is a valid kernel. So, and this can be useful for classification or as a similarity measure as it increases exponentially with the intersection, so it highly rewards overlaps. Therefore, we have seen that this unusually defined kernel is a valid kernel, and we can use it for a non-vectorial objects where using this operator newly introduced here, we can transform these objects into characteristic vectors with which we can then perform this feature mapping dot product and calculate their similarity. Or we can do it right away. We do not need to go through this Kronecker product, just observe the amount of elements in that intersection, and that will be the exponent for the base of 2, and with the knowledge that we can always resort to this formulation, and that will mean that it will be a valid kernel. We have discussed the difference between generative models and discriminative models. Generative models will typically be governed by some probability distribution of our random variable, and this probability distribution will be characterized by certain parameters. Like, for example, in case of normal distribution, which could be characterizing certain random variable, we will have the parameters of mean and variance, or in multidimensional case or multivariate case, a mean vector and a covariance matrix. Now, these generative models are great for tasks where we have, for example, missing data, but overall their performance on, let's say, a classification tasks is considered not as good as discriminative models. So one would like to take the benefits of generative models, like dealing with missing data, and utilize these benefits in discriminative tasks. And one way to do it will be to generate a kernel from this probabilistic generative model. So imagine that we have a random variable x, which is having a probability distribution of px. Now, for random variable x, we have a specific input vector, as this is a multidimensional random variable x, and then another of such a vector x prime, and we can generate a kernel which is a product of px and px prime. Will it be a valid kernel? Well, this is a product of two probability distributions, and if we say that our feature mapping is a simple scalar function, and this scalar function is actually corresponds to the probability, then its product of these two feature functions, feature mappings, will be the product of the two probabilities of these two inputs. So therefore, this is a valid kernel. And this valid kernel is in fact measuring something which we could call typicality in case of high probability of x and high probability of x prime. Both of them are very probable, and therefore we will have a high value coming out of this product. And so that would say, that would express that both of these inputs are quite typical, and if one of them will be not having high probability, or both of them do not have high probability, then we will have a low value, and we would therefore say that this is not a very typical scenario given the probability distribution. So it somehow can express similarity for some scenarios. Now let's take this kernel as a simple kernel, and let's extend it by the rules where, for example, if we multiply a kernel by a constant, it is still a valid kernel. And we can see that if we now abstract for a short while from this sum here, that we have a probability distribution, which is here conditional probability of p of x and p of x prime given I, and we multiply it by pi. And then in this case, if we are not really now iterating over the I, it will be just one value, and therefore it will be a constant. This is one way to extend it, and then we can also extend it by taking all such products of conditional probabilities with the marginal probability of I and sum it up, because we have a rule that the valid kernel summed up with another valid kernel will still be a valid kernel. Therefore, we have here a expression where we are somehow measuring the probability of x and x prime given I, and we can think of it as that I is some latent component index, for example a mixture model index which is indexing a particular component. Like, for example, in the Gaussian mixture model, it will be indexing a certain Gaussian component. Like we can see then that if we are dealing with one Gaussian component which has a probability of I, so this will be like the pi mixing coefficient, then the probability of x in this given this Gaussian component and x prime given this Gaussian component, if it is similar, then so if it is similarly high, then we will have a high value coming out of this product here. And then in other cases of other Gaussian lobes, we will have some different values associated with this product term. And we can say that this similarity measure evaluates how likely x and x prime are under the same latent component I. So how do they behave under the same component? Are they behaving in the same way, or are they behaving differently under the same latent component? So the two inputs will give a large value for a kernel function and hence appear similar if they have a significant probability under a range of different components. So that's a similarity measure which can be expressed in this setting where the I is some later component index. And this discrete case we can extend to a continuous case where we will have the probability of x given a certain latent variable z, and we can see that the formula is essentially the same, except that it is a continuous case and the latent variable z is now a vector. So we also can consider that it is not only these two input vectors are weighted just by one from one perspective, like for example mixture model index, but from various perspectives which are characterized in this latent variable z. Our final example of the construction of kernels from probabilistic generative models is about extending the same kernel which we have seen on the previous slide and applied to ordered sequences of length L. So here in this case we will have input vectors x1 to xl organized in a sequence capital X, and that is our one input sequence, and then we will have another input sequence capital X prime, which also have L input vectors organized in a sequence. So this is also another input sequence, and there is a popular a probabilistic model called hidden Markov model, which expresses the probability of X as a marginalization over a corresponding sequence of hidden states Z. And as such, therefore, we can formulate the similarity measure between two sequences which are generated by the same hidden sequence Z by the product of the conditional probability of the first input sequence given Z, the second input sequence given Z, and the probability of Z. And in this sum we go over the all hidden states of Z in order to calculate this similarity of these two sequences. So we can see that such kernel concept can be useful in order to utilize the probabilistic generative models and create a similarity measure which can then be utilized later in some approaches which are of discriminative character, as we will see later. Another way of utilizing the probabilistic model for a similarity measure using constructing a kernel can be seen in the so-called Fisher kernel. So it is a similarity for two input vectors obtained by parametric generative model Px given some vector of parameters theta, like for example mean and variance for the normal distribution, and it defines how similarly two data points influence the parameters theta of the generative model, and this is therefore expressed in a gradient of the likelihood or log likelihood function with respect to the parameters theta. So not with respect to weights as we are used to, but with respect to the underlying parameters. So, and it basically defines us a gradient function g that is used in the Fisher kernel. The simplest Fisher kernel will be simply the dot product of the gradient at point x with respect to the parameters, and for the x and for another input vector x prime. And we will see that this is a similarity measure, because it's not a similarity measure about really about the values, but about the gradients. So it somehow says, if we regard this as the phi, the feature mapping function, that if the phi of x and phi of x prime point in the same direction, they both push the model parameters in a similar way, and therefore they are similar. So we can see that it's the first order derivative somehow has been utilized here as the similarity measure in this Fisher kernel. Just for completion, this Fisher kernel typically would contain a Fisher information matrix F, which is an expectation of the outer product of so it's an average of outer product of these gradients, and for all x, and it's an expectation with respect to x, or we can see it as also an average of these outer products for all for the entire training set. So this Fisher matrix is used for the purpose of to be invariant under nonlinear parametrization of the density model, meaning if the parameters of the probabilistic model are non-linearly transformed, it will be this kernel utilizing this information matrix F or its inverse will be invariant to that. So we see an example how a probabilistic model is used here, but not as the directly measuring the probability of two inputs and their product, but actually a gradient of these probabilities with respect to the underlying probabilistic distribution parameters. The final example is the sigmoidal kernel. So we can also have a sigmoidal kernel, unlike the previously defined exponential kernel for the radial basis functions, for example, as we will be talking about them next, or the polynomial kernels, but we can also have a 10H based kernel where we have the dot product of these two input vectors multiplied with a constant and with an added bias as an argument of a 10H kernel. It is important to note that this kernel is not always leading to a Gram matrix which is positive semi-definite, although it is still used in practice, and it is related to the support network support vector machines, and as we will see later, and as we are using the 10H, which is typically used in the hidden units of the hidden layer, we can see that it resembles similarity to the neural network models. Next, we will be discussing the radial basis functions, also from the perspective of kernels. So, radial basis functions were originally used in functional interpolation, and the idea was that we have a set of input vectors in some multidimensional space x1 to x capital N, and we have corresponding values t1 to tn, and we would like to interpolate these points with some kind of a smooth curve. And typically the radial basis functions will have the form that they are having a certain center. That's why they are having this association with a certain radius, and a certain distance from the center will be essentially governing the performance or the behavior of these basis functions. So the offset or from the center of the basis function will be basically the argument for our radial basis function, which could have various forms, and typically it might be the Gaussian radial basis function, for example, as we have seen before. So we have seen it before in the case of regression, where in the regression case we had fixed basis functions. So we defined for them some centers, and we defined for them some of the characteristica of their spread or variance or covariance matrix. And then we trained some weights. So that was done here in the case of regression, again, that we had some function, this radial basis function, and we trained the weights Wn, which were then used for defining as this regression function. And if we used the n of the radial basis functions, capital N, meaning that we had each above each input point we had one basis function, that would lead, as we have seen before, to an overfitting. So while this might be desired in the case of function interpolation problem, because we want to interpolate the function exactly on those sample points which are defined, in the case of pattern recognition, this might be considered as overfitting and might not be desired. So we have seen previously that we found these coefficients Wn via least squares, and if we wanted to have define a regression function such that we are not perceptible to the noisy target values, then, and by that we do not overfit, we introduced a regularization. So the error term which was used in evaluation of the fit would be having additional regularization, which would lead to then functional approximation instead of functional interpolation, and would lead to more smoother representation of the regression function, even in the case that we will have above each of our input training points one radial basis function. Let's discuss an approach which is called the Nadaraya-Watson model, which is related or is describing radial basis functions, but more from a kernel perspective. So here, as we have seen also on the slide before, we had this function h, which can be regarded as a kernel, and that kernel will basically characterize all our training data, which should be considered in an estimation of a point at a new location x. So we want to interpolate, but now we will be considering that we have actually a noisy input. Imagine that under noisy input, you could understand that you would like to point to some input point, let's say to a training point location, but you actually are not precise enough, and you are pointing to some point nearby. So if we have our training points xn, which are the true training input values, we can have some input x which is nearby, and it is characterized by the random variable xi, which has some distribution which is described here by this xi. So we can formulate now our error function as the integral of the training set. However, here the training input data points are slightly perturbed by this random variable xi, which of course would have a mean at 0 and will have a certain spread characterized by this probability distribution ni of xi. So we integrate this error term with respect to where we weight each of these squared difference with a probability of xi, and we go over all of the xi to determine the error. So we have here an inner loop, if you like, of over all xi's, and here we will have the outer loop over all training data points, which will be then characterizing us this overall error. Now we can characterize that our input point is this noisy x, which is xn plus xi, and we will use the calculus of variations to determine the function of y by basically performing the partial difference of the error with respect to the function y by means of this calculus of variations. So without going too much into detail, that leads to this squared term is now a linear term, as we are used to, and it's cancelling out the 1/2 because we are performing the derivative with respect to the function y, and then, except of this probability distribution, which is unchanged here, we have here this Dirac delta term, which is coming out of this derivative, and that leads to the fact that we are essentially picking out just one value, because this will be 0 for all the xi's except of when the xi is equal to 0, and that leads to the fact that we have now just taking out the our regression function with the noisy input, and then we have our probability distribution ni, where we have our xi represented here by the x minus xn. If we set this to 0 by means of finding the minimum, then we have the following representation, where we simply put on each side of the equation either yx or tn, which we can see here, and that leads to the yx function to be equal to this multiplication of all the training targets with the probability distribution, where the argument is x minus xn, so that's the distance from the center, where the xn will be forming the center, and here in fact we will have some normalization term. So as we can see that the ni is both in numerator and denominator, this is normalized, so the sum of all of these kernels, so we can regard this fraction here as a kernel h, the sum of all the kernels will be then equal to 1, and because of this normalization term. So all of the contributing basis functions will be contributing with some fraction to the final interpolated value, and overall their contribution will be 1 Now that's the model of this radial basis function, which is called the Nadaraya-Watson model, which we will also derive in a slightly different form in the next as well. However, before that, let's have a look at what is meant by these normalized kernels. Please keep in mind that here in this function we do not have the w's. For the function y, we didn't train any weights. What we trained is the relationship of the x with respect to all input values and their target values that we which we memorized, and that is represented here by this kernel, and is as it is this memory-based method. So here we can see the comparison of Gaussian basis functions with respect to the normalized radial basis functions which we have learned, which have been coming as a result of these normalized kernels of these functions Ni, which are the probability distribution of our input noise. And we can see that at each location on the x, we will have not that the weight itself will be 1, but the sum of weights. So let's say at this location, we will have this weight, let's say equal to 0.8, and this weight will be equal to 0.2, and together it will be 1. So everywhere at each location, these otherwise kernels with their mode at the same location will be normalized so that the overall sum of the kernels is equal to 1. So that's the difference of these kernels with respect to some Gaussian kernels which will be fixed, and then we will be training the weights which will be capturing this learning process. Here, the learning process is captured in the actual kernel. So, as we have our basis functions, even in this model, associated with every data point, because we went through every data point in the sum, and there was a corresponding Tn multiplying the kernel. These models are costly to evaluate at the inference stage when we are predicting new data points. So therefore, it alternatively might be that we actually, instead of choosing all endpoints, we just choose endpoints and perform the interpolation based on these endpoints. And this can be done in various ways. One can be done in such a way that we have a randomly we choose m input data points, so that is one approach. Then another approach could be, which is called orthogonal least squares, where we take these points sequentially, where we have an error function, and with this the error function will, as the sum of square differences, will be reduced by integrating one more point. So we have an functional estimation, and with which we can improve with adding one more basis function point. And we always choose in each iteration the basis function point which reduces the sum of square differences most. So this is called orthogonal least squares strategy. So here we still choose the points which are above the particular all the input sample points. So we are not choosing centers of these radial basis functions somewhere else than above the training data points. Then we have the third case, which is based on k-means clustering. So we can cluster our input data into k clusters, which will define k basis functions, and the centers of these K clusters will be defining as the basis function centers. So here in this case, we are no longer above the training data points. All these strategies can be in principle applied both to the parametric approach where we are learning the weights, or also to the non-parametric kernel-based approach where we are defining a kernel based on the training data set.
In the following slides, we will devise a formulation of the Nadaraya-Watson model, which is a model which defines as a kernel function. So we already had one way how we devised it in the previous slides, and it relates to kernels like we already first encountered the equivalent kernel notion in the case of linear models for regression. There we learned that we can devise a kernel which is then with a linear combination of the training set of the target values Tn, we can then get the linear regression for outcome for the new input x. So we will get the value y, which is itself the mean of our conditional probability distribution of the t at the position x, and it will therefore also be corresponding to the conditional expectation of t given x. Now we will devise a Nadaraya-Watson model, the kernel, from the perspective of the kernel density estimation, and we will be using the joint function x and t function, which will be the component density function. So imagine that if x is t-dimensional, t is one more dimension, so it's t plus one dimensional input into this, this function operates in t plus one dimensional space, and it basically is some kind of a fall-off function. So at the value 0, if all the components 0, it will have the highest value, and the more far away from the 0, it will have a lower and lower value. And if it will be, for example, this Parsons window, then it will have values equal to 1 between minus half to half. It will create some kind of a box of equal density, and then everything outside that box will be equal to 0. So that is one type of kernel, but that's very discrete. We could have, for example, also an exponential function which will create this kind of Gaussian blob as this component density function. Now, if we want to define the joint probability based on this function, we simply sample our space with the input vector x. We want to know what is for the n x and the given t, what is the probability at that location, and that is related to how many other points xt pairs are in the neighborhood, and what are then how far we are from those training set points. And if we are very close to them, then the density is high, and that will mean that the probability of such a point will be high. If there will be not many training points in the neighborhood, by the training points we mean both input and output, then the probability will be low. So we are evaluating with respect to the distance from all the training pairs, what is the function of these offsets, and then we are summing it up and averaging. And that will be the probability of this joint distribution. So if we have this joint probability distribution, then with the joint probability, we can express, in fact, the y of x of this new input point, which means that it is the conditional expectation of t given x, and that we know that it can be defined by this integral where we have the t probability of t given x dt. But we do not have the probability, the conditional probability. We have the joint probability, but we can replace this conditional probability with its formulation with joint probability, which is here, where we are in this case we are calculating out the marginal probability px, dividing the joint probability by that, and then we will get the conditional probability of t with respect to given x. So that can be formulated or reformulated in such a way that we have here the integral which contains the t, and it's the integral of the joint probability, and basically integral which performs the integrates out the t, and in this case here we have the marginal probability p of x expressed by the form of the integral. So these functions, following these formulas, we can find out how can we obtain the kernel from this kernel density estimation perspective. Continuing here, where we are recapitulating again that y of x is equal to this conditional expectation, which is now formulated by the joint probability and the integral, and here we have the t as it is defined in the formula for conditional expectation. Now we already know what is this probability, and this is in fact the sum of these functions normalized divided by n. Now we can put the integral inside and have basically on both numerator and denominator the same formula, except that here we have the multiplication with the t. And now what we will do is we will substitute the interval t minus tn, which we have here, by some variable u, which will then mean that this integral this integral here will be fx minus xm, and then the second component will be the u and du. So because we have here it was dt, and the dt we replaced by we expressed the dt with respect to the u, which was u plus tn, and then if we integrate it, we will end up with du. Now we will say that this integral of the function f xt dt, so this marginalization will be equal to some function x. So this means that we are imagining that this is this Parson window, this kind of kernel, this kind of follow function, which is also even function, and we are now just marginalizing, so we are integrating out the t, and so that it is only function of x. And so imagine that we are kind of summing up all the t dimension and kind of projecting it onto the x dimensions, and that will be the result of the gx function. Now if we are have changed this formula here, we can see that this is therefore, if we express it by the function g, will be equal to g x minus xm, because here we have a certain offset we are integrating just with respect to u here, which is not really having anything to do with the axis. Therefore, here is some arbitrary x, and then fxt dt, here is basically the same thing, will be equal to gx, so in this case gx minus xm. So it's just a replacement here, which will be important for the next steps, where here we will be therefore changing the variable, and we have changed the variable so that we have here this formulation. Instead of the t, we have now u plus tn, because the tn goes on the other side. So here is u plus tn, and then f x minus xn u du. And here already we have the integral margin. We solve the integral. We have the function g here, and we have the sum as it was here before. Please note that we have also got rid of this 1 divided by n from both numerator and denominator. Finally, as the next step, we can see that this leads to two integrals, except of that it's many integrals in this sum, but within this sum we have two integrals, and one is u times fx minus n du, which is again the gx minus xn, so that's the result of the integral, multiplied, and then we have tn times this formula where the tn acts like a constant. So this will result into the outcome tn gx minus xn. And the u times this function is equal to 0. And why is it equal to 0? Because this function is basically even function, and if we are integrating this even function multiplied with obviously an odd function t, it will be an odd function. So everything from the negative side will cancel itself out with the positive side, and we will have at the end 0. So this is, here it's t fxt dt, here we will have u fxu du, but what's the name of the variable doesn't matter that much. It's the same outcome. Here will be 0. So we are reaching the formulation here that we have this sum of tn times g x minus xn, and this is normalized by this sum of gx minus xm. So in that case, we can reformulate it as again, like we had in the equivalent kernel case, kernel x xn times tn, and in the sum, which where the kernel x xn is equal to the function g x minus xn, and divided by all the sum of all these functions over all the training input points. So we can understand what is this g is again some kind of a kernel, but it's not a kernel in the x plus d plus 1 space, but it's a kernel in this space because we have collapsed the t dimension onto the x dimensions, so it's a marginalized form. And in this form, this also will therefore act as a kernel, and this formulation here is exactly the same as we had before with the formulation where we had this function me a couple of slides back. So we can come to this result of this Watson model from the formulation of our conditional expectation and of the kernel density estimation function, which might be normalized, but it doesn't have to be normalized, because at the end it will be normalized by this term here, so that the sum of all these kernels over n training points will be equal to 1, which can be very easily seen, because if we go over all of these points with the Tn, if the training set will be just 1 here, then it will be the same thing in the numerator as in the denominator, and then the sum of these all kernels will be equal to 1. So we have now expressed what is the conditional expectation equal to, and we have again devised this notion of this equivalent kernel with this Nadaraya-Watson model. But in fact, we have also expressed not only the conditional expectation, but we also have devised the entire probability distribution of the t given x in the following way. So we have already before expressed that this the pxt, this joint probability of input and output training set pairs, is this function, this kernel function, which we have, and the sum of all the kernels are normalized, but the conditional probability is equal to the joint probability divided by the marginal probability expressed here by this integral, and therefore we have all the probability distribution for the t given x. So at a particular position x, we could say that here is the mean of our conditional probability, meaning our expectation, but we can define at each position within this column of given x by fixing x, what is the probability of a given t. And here we can see also that there is a certain standard deviation plotted around this regression by using the kernels. Before we finish describing this image, let's finish describing this formula. We can see that here we have the joint probability, which is expressed here. The 1 divided by n has been on both numerator and denominator, so we cancel it out. And here we have this this integral over all so here we have the sum of all the functions, and here we have the sum of all the integrals. So we are integrating out the t and collapsing this function f into this g function, which is projecting the d plus 1 dimensional kernel kernel onto d-dimensional kernel, and that is then summed up here for each of the training set. So we can have, for example, kernel like this, which would be a 2-dimensional joint probability of x and t. So here the x is not a vector, but it's a scalar. It's 1-dimensional, so that it corresponds to this image. And this function itself is already normalized, because here we have the normalization factor. But it doesn't have to necessarily. This kernel will be normalized also at some later point if we will be expressing it in the formula for the probability. So here this kernel has been applied in this plot, where the kernel method of this Nadaraya-Watson model was used for calculating the conditional probability for each x and also the mean from these training input points. So observe that our radial basis function kernel has been placed over the position of each x t coordinate, that's in the center, and that is forming us our kernel. And here we can see that it's kind of very anisotropic, but that's just an unfortunate artifact of the scaling factor. We can see that this is ranging between minus 1.5 to plus 1.5, and we can see that here we go between, so which is in total 3. Here we go just between 0 and 1, which is 1. So this one is kind of 3 times squeezed, and therefore these otherwise very circular notions of our kernels are now squeezed into these kind of elliptical ones. But if our plotting will be preserving the aspect ratio, then so meaning that the same distance here will be the same distance here or within the same values, then it will be, these kernels would be circular. So with this, we have devised this Nadaraya-Watson model where we can generate this through these kernel functions a regression, and we can obtain with the maximum likelihood estimation of the y, the equivalent result with this, or we can also say the conditional expectation, but not only that, but we can also assess the any t at a given location x, what is its probability. Next discussion on kernel methods, we will discuss the framework of the quotient process. First, we will just recapitulate what we know already from the linear regression again, where we know that linear regression is a linear combination of m basis functions, which is weighted by the weights, and the weights are defined to be around the 0 and with a certain normal distribution and standard deviation from 0, and forming an isotropic quotient, so that we can see the following formulas, which we already know and will be basis for our build-up of our quotient process framework. So our regression function y given an input x, we will calculate the feature vector, which is and then linear combination of the feature vector entries with the weight vector entries leads to a weighted by the weights entries leads to the a regression value y, which is the mean of the target value conditional expectation. Now we have the prior of the weights, which is a normal distribution with a mean 0, and it is an isotropic quotient with alpha serving as the precision of our weights probability distribution. Now the idea in the quotient processes is that this probability distribution will induce the probability distribution over our functions y of x. So far we didn't really have the functions of y of x expressed in this way, where we would be expressing the y of x from a probability distribution based on the probability distribution of the weights. So we will see how that comes to place. Let's discuss that our y for our training samples will be given certain values based on the input vector from x1 to xn. We will have a different values y1 to y capital N. And these values can be essentially calculated by the design matrix multiplied with the weight vector. So we can see here this formula is getting in this vector notation this shape. So where the design matrix itself is has the elements which are phi, capital Phi and k, such that we have on this location in the design matrix, we are having the kth feature function of the nth input vector x. So we have this design matrix again has rows of different input vectors and the columns of different feature functions. So and multiplying this matrix with the weights will yield the vector y for all the input vectors. Now the probability distribution of py is therefore based on this, and based on the probability distribution of the weights. The probability distribution py is a linear combination of quotient distributed variables given by elements of W. So linear combination, because we have a linear combination here expressed by this matrix vector multiplication. So we have this quotient distributed variable given by the elements of W, and we perform a linear combination of this probability distribution, and that leads to the probability distribution P of y. And therefore, as it is P of y is a linear combination of a quotient distribution, then that's why it will be also a quotient distribution. So we will have a normal distribution of y. And now let's have a look what exactly will be that value. So probability distribution of a function y of x can be seen as that the y of x is a stochastic process specified by giving joint probability distribution to any finite set of values y with x1 to x capital N in a systematic way. So we now know that P of y is a normal distribution because it's a linear combination of the quotient distributed weights values. So therefore, we can express that if we know that this is a quotient, we need to find out what is its mean and what is its covariance matrix. As this is a multivariate variable, therefore we will have here a covariance matrix and not only a simple variance. So the expectation of y can be calculated as the expectation of the design matrix times the weights, which here this one is the random variable following probability distribution, and therefore this design matrix phi can be taken out of this expectation, and we have an expectation of W which is equal to 0. Now we have the covariance matrix. The covariance matrix can be calculated as the expectation of the outer product of the y's, y vectors, and that is equal to, so we replace the y again with capital Phi times W vector, and again we can take out the phi and phi transpose, because the y transpose here leads to a phi W transpose, which is W transpose times phi transpose. to this formulation where we have now the phi is on the left and phi transpose on the right side of the expectation of W transpose, and this is actually the covariance of the covariance matrix of the prior of the probability distribution of the weights, and it is equal to a powered by -1 times the identity matrix. So in that case, we can reformulate it as the design matrix times design matrix transpose, and there was then a powered by -1 times the identity matrix. The identity matrix is playing no role here in this matrix multiplication, and here we can take out the alpha powered by -1 as 1 divided by a in the front. And we can call this that this is a certain matrix K. So this matrix multiplication and multiplied by this scalar is a matrix K. And if we look at what are the entries of this matrix K, we will find out that the matrix K consists of the entries of a certain kernel function given by these design matrix entries, so which are the feature which corresponds to the feature map of the training set. So we call this matrix K the Gram matrix, and this will be an important matrix from various perspectives. And the Gram matrix is simply having the results of applying the kernel function to various combinations of our values x, like for example here x and x prime. But for example, if we want to know the element of the n-kth element of this matrix K, it is equal to the kernel function xn with xm, and that is equal to the phi xn transpose times phi xm. So these are the entire feature vector feature map of this feature transformation of this input vector xn, and entire feature space transformation of the input vector xm. And this is then scaled with this reciprocal of alpha afterwards. So this is the entry for our in the matrix K, and we can observe various aspects here. So first of all, if it's the feature times feature itself, then this will be simply squared of squared value of our feature vector of our particular input vector, and this will be on the diagonal. And then we have also another observation that kxn xm is equal to kxm xn. So this will be in fact a symmetric matrix, because this multiplication here is in fact, this dot product here is commutative. So we will have a symmetric matrix, and we can choose this kernel to be generated by these feature vectors. But in fact, as we discussed in the constructing kernel section, we can have arbitrary kernels. We do not need to have them constructed by these feature maps. and feature vectors product, we can simply define any kernel that satisfies the condition that our gram matrix K will be a positive, definite or semi-definite matrix. So that means that its eigenvalues will be positive, or for semi-definite positive or 0. So for example, the exponential function, which with a square difference of two input vectors will satisfy such a condition, for example. There is another kernel, so this is a Gaussian process kernel, and this is, for example, another kernel, which is called Ornstein-Uhlenbeck process kernel, and this has slightly different value. It's also an exponential function, but not of a square distance, but simply an absolute value of that distance. And interesting fact is that we can generate then from this kernel function the actual gram matrix K, which will serve as our covariance matrix, and we have our distribution with a mean of 0. So in fact, our Gaussian process probability distribution over functions y of x has a 0 mean and has covariance matrix K. So that can be considered as a probability distribution of the functions y over the functions y before we have seen any target values t. So we haven't seen yet any target values t. We have only seen the input vectors x, and we are making predictions how the functions y can look like. So we will see that on the next slide. Here we can see the two previous kernels, the Gaussian kernel and the Gaussian process, and the Ornstein-Uhlenbeck kernel and the Ornstein-Uhlenbeck process, which is plotting several functions y. And they are simply these functions y are drawn from this probability distribution, which is a normal distribution, multivariate normal distribution of a random variable y with the mean of 0 and with the covariance matrix K. In this particular case, we have generated a lot of input training points xn, which were defined very densely on this interval -1 to 1. And we did the same here. So we had, let's say, 100 values of xn here, and those 100 values of xn we used for constructing the gram matrix K, and we also had the hyperparameter alpha, would have the hyperparameter alpha if we would start from the feature map, but we can, in this case, we didn't start from the feature map because we directly used the kernel, which was the Gaussian kernel, and we calculated the function K for each pair of x1 with x2, x1 with x3, x1 with x4, and so on. We generated this 100 times 100 matrix, and then this 100 times 100 matrix K was used for defining this multivariate 100-dimensional Gaussian distribution in a 100-dimensional space, and there we simply picked a one sample, and this one sample had then 100 dimensions. This one sample y would have 100 dimensions, and these 100 dimensions will be corresponding to these dimensions of x. So for every pair of x and so let's say x1 and y of x1, we would plot the x on the position x, we would plot the corresponding y. And so we have simply drawn, in this case, 1, 2, 3, 4, 5 different vectors y, which were 100-dimensional, and we simply connected those individual values y, and we realized that we have that this is forming as a smooth curve. So it is given by the actual kernel how smooth these functions will be, because it will define how well correlated the neighboring values which are close to each other, the input values are. And we can see that for Gaussian kernel, it results into smooth functions, which are random functions, but they are smooth. And in the Ornstein-Uhlenbeck case, we have not very smooth functions, where you can see that they are much rougher. And although they are both exponential functions, but here we have a square of the distance, and here we have the absolute value of the distance, which causes us this rough representation. And this kernel has been also used in the was introduced to describe a Brownian motion, and we can see that it acts. These motions is quite erratic and looks like indeed like a random walk. So the Gaussian process is the probability distribution, generates as the probability distribution of the function y, and it is a normal distribution with the zero mean, and the covariance matrix is governed by this grammar matrix K with the entries from the kernel function of the input vectors x1 to x capital N. Now, the next aspect to consider is to consider the noise. The noise is independent from this randomness of this choice of the function y, and therefore the observed target variables Tn will be governed by the formula where the Tn is equal to the regression function evaluation at the training input point xn plus the epsilon n, which represents the noise. And we can say, as we learned before, that the probability distribution, conditional probability distribution of our training target outcome with respect to the y of xn is a Gaussian distribution, conditional distribution, where which is characterizing the noise around the mean y of xn, and the noise has a precision beta, or it has the variance beta inverse. So this is a single variate Gaussian distribution, which characterizes the spread of the likelihood of how far the target outcome is from the mean. So, and again, so we are here characterizing a probability distribution of t with respect to y, and this is just for one training set, training point. However, if we observe the joint distribution of all training points, T1 to T capital N, conditioned at the values, on the mean values, y x1 to y x capital N, then we can express the conditional probability of this joint distribution of T conditioned on the vector y is the normal distribution as a multivariate normal distribution with mean of y and with the isotropic covariance matrix governed by this variance beta inverse multiplying the identity matrix of the dimension n by capital N. So we can see that this is like a conditional probability, and we can see that the py in fact is a marginal distribution, marginal probability of the y, and it is a normal distribution of with the mean 0 and with the covariance matrix K. So if we have the marginal probability and conditional probability of t with respect to y, we can express the marginal distribution of p of the target values. And this we can do by solving the integral where we integrate out the y. So, and this is this integral solves a linear Gaussian model, because we can observe that here we have a certain Gaussian function and Gaussian probability distribution, and this random variable y is used as the mean, and this random variable is itself Gaussian, and it is transformed by a matrix A and with an offset B. So we can see that here, where we have one probability distribution P of x, which is a normal distribution, and then we have a conditional distribution y of given x, where we have the linearly transformed x by the matrix A plus B. So the probability distribution of y in this case is also a Gaussian with its mean A mu plus B, and with its covariance matrix L inverse plus A capital lambda inverse A transpose. So we will apply this, what we learned already from the probability distributions earlier. We will apply it in this case. So where the x will be in our case the y vector, and the y, which is confusing, will be the t in this case. And we can simply see what will be this integral. So this integral will simply give us the marginal probability distribution of t, of the target variable, and that is governed by this formula will be the mean. And let's have a look. So what is the mean? So mu is coming from the prior or from the marginal of the x, which is here, the mu is here 0, and then we have a, which is coming from here, the A is identity matrix really, and B is 0. So identity matrix times 0 plus b is equal to 0. So our marginal distribution with respect to of t is a normal distribution with mean equal to 0, and the covariance matrix we will call C, and we will see what the capital C covariance matrix is. It actually should be L inverse. So what is L inverse? We see it here. This is in the conditional probability. L inverse is in our case the beta inverse times identity matrix. So that's what we have here, beta inverse times identity matrix, and then plus A lambda inverse A transpose. A is identity matrix, A transpose is identity matrix, so we can ignore them, and therefore we have only the lambda inverse. Lambda inverse is here, and that is in our marginal with respect to y is equal to k. Therefore, our matrix C, which is the covariance matrix, is simply the Gram matrix plus the identity matrix with multiplying or scaled by the variance, isotropic variance, where on the diagonal instead of ones we will have the beta inverse for all rows or columns. So therefore we can say that the entry C and M of this matrix C is simply the entries of xn and xm input vectors, and that corresponds to the Gram matrix part, which is the kernel function evaluated for these two, and then plus the beta inverse entered with the Kronecker delta, meaning if n and m are equal, then this is equal to 1. If they are not equal, it's equal to 0. So this part will be only added on the diagonal, otherwise the C entries are equal to the K entries. And it is somehow, we can understand it, that these two are independent random processes which have independent covariance matrices. So two independent Gaussian sources of randomness, in their covariances simply add. So we can see that these covariances have been simply added. So at the end, our probability distribution of t is governed by the normal distribution with again the mean 0, and with the covariance matrix C. Now this might look a little bit odd, because why should the t be having the mean 0? It depends on its on the training data values. However, this again expresses a probability distribution before seeing the actual training set. It's the estimate of the training set with its kernel, and we know that the kernel is expressing how correlated the input values are based on how far they are from each other, and then the beta, which characterizes the variance of the target outcome from the mean value y, or from the conditional expectation. So this is a probability distribution of t of if we haven't seen the actual training target our values yet. And we can see the outcome of the of these random distributions here. We have here slightly different kernel. So this kernel here is having an exponential component which has the square of the difference between the two input vectors, and it is having the theta1 parameter as the precision of this exponential function, and it is multiplied with the theta 0, which is simply scaling the outcome of this exponential function, and then we have some constant term added, and then we have some linear kernel term added, weighted by this theta 3 parameter. So we have 1, 2, 3, 4 parameters which are characterizing this kernel, and we can see that this is definitely a kernel because this function is a kernel. Exponential or multiplication with a constant of this function is a kernel. Exponential of this argument is therefore a kernel. Constant multiplier of this kernel is a kernel. Then addition, when added with another kernel, is a kernel, and another kernel, which we know that this is a linear kernel, is also a kernel. So this is definitely a valid kernel leading to a entries of the Gram matrix, which will then be as a result positive definite. Now let's have a look how the our random probability distribution of the y looks like given different of these parameters. So these are again still functions y, and again we have here a lot of training input data, and we are simply then plotting the values of y corresponding to the axis and connecting them together, but as they are so densely populated, we do not see that like linear connection, because they are just very closely next to each other and show us nicely the behavior of these randomly picked functions. And we can see that these are the first parameters, so the theta 0 is 1, and our precision theta 1 is 4, and then we have, if we change this multiplier to 9, we see that our original spread is between 1.5 and minus 1.5 is now 4.5 and minus 4.5. So it has increased in the y dimension, and then here we would be making much more higher precision value, and we see that these functions start to vary much more. Now we decrease this precision, and we see that we have much more smoother functions y. Then if we are adding this constant term, we see that this leads to much more spreaded random functions. And if we add this linear term here, we can see that these functions are no longer oscillating around 0 or with an offset, but instead they are having some profile which are like increasing or decreasing. And then once we have these functions, we can, if we want to create a synthetic training set based on this type of kernels, we can simply sample at each location. So we can choose one of these functions, maybe this blue one here has been chosen, we can see here, and then we are sampling at each location x the probability distribution governed by the variance beta to find the corresponding values t. So this will be here we will have the added noise which is associated with the target values. And therefore these points here which we have obtained will be creating us a valid training set T, or which is following this random distribution of the randomness of this function y given by the kernel matrix, Gram matrix, and the beta probability variance of the normal distribution of our noise. So, but now we still do not really have the T. We actually want to use our Gaussian processes for linear regression, however, and not for generating just some data, but actually to estimate what is the value of a T for a given value X. So let's have a look how this can be done. So first, what we would like to find out is a predictive distribution. So this predictive distribution is equivalent to the distribution, predictive distribution, which we obtained by the parametric approach, where we have defined the where we have used the fully Bayesian treatment, where we defined the posterior distribution of weights and multiplied that with the conditional distribution of t given the x and the weights, which led to the probability distribution of the t given the prior and our data. Now, this will be we will have an approach which results in the same equivalent probability distribution, but from the perspective of this Gaussian process. So what we will formulate now, we will be looking at the conditional probability of Tn plus 1 given the training set Tn, and also the target value as well as the input value. So the X capital N is not here, but actually it is based on the training set and plus the xn plus 1, which we call this one point which doesn't belong to the training set 1 to capital N. So, but now we simply first formulate the probability of T capital N plus 1, which is governed by the normal distribution with the mean 0 and the covariance matrix Cn plus 1. Now let's think of what this Cn plus 1 looks like. If we have the matrix Cn, this matrix Cn will be, with respect to the Cn plus 1, will be in the top left corner, and then we will have one more column and one more row. And in this one more column, what we will have, so here are all the combinations of the input vectors or kernels plus the, eventually on the diagonal, plus the beta inverse. And it will be for the x small n going from 1 to capital N, will be forming this C capital N. And here, this column will be basically the evaluation of the kernel of xn for each row with x capital N plus 1 with our new point, and it will be, here is the xn, this one will be x1, x2, x3, x4, x5, and so on until xn plus 1, and this is the k transpose. Actually, this will be until the kn reaches the value x capital N, and then the last value c here in the bottom right will be simply the kernel x capital N plus 1 and x capital N plus 1 plus the beta inverse. So now we see how we have extended our matrix Cn into matrix Cn plus 1, which is the matrix which is governing our normal distribution, the shape of this normal distribution for our random variable Tn plus 1. And now the key idea is that this conditional distribution Tn plus 1 of given Tn is equal to a normal distribution again of a certain mean and a certain variance. In this case, this is a scalar, therefore this is a scalar, therefore this is a single variate normal distribution of a mean and scalar value and the variance, which is a scalar value too. And now we need to find out how do we calculate this mean and variance. Keep in mind that the marginal distribution of the entire joint probability is described here, and now we are expressing the conditional probability of the Tn nu t given the training set. And this is the mean, and this is the sigma. And how did we come to these values? So these values are coming from the fact what we had before, again in the probability distributions of how we can calculate conditional probabilities of random variables, which are originally forming as here we have like a random variable x, which is a vector, and it consists of a subvector xa and subvector xb, and therefore with that this is normally distributed multivariate normal distribution with a mean, and then the mean corresponding to xa is mu a, and to xb is the mean is mu b, and then we have the sigma is our multivariate covariance matrix, and we can partition it into sigma AA, sigma AB, sigma BA, and sigma BB, where the sigma BA is AB transpose. And in there, we had several equations, and which are in chapter 2. You can go and review it if needed. But there we have a conditional probability of A given B, so where the A is one part of the vector and B is another partition of this vector, is equal to this term. We have devised it, and the covariance matrix, or in the case that one is just one element, the variance is governed by this formula. So we have already this kind of a template, and we can use this template on expressing our normal distribution, this conditional probability of Tn given Tn plus 1 given the Tn. So that is, now we need to find out what is the mean and what is the variance based on this formula which we have devised earlier, and now it becomes handy. So keep in mind that mu A given B will be expressing us the Tn with respect to Tn plus 1. So we are interested in the opposite, which is very simple by seeing this matrix kind of reverted, like as if this would be the first element and the first element in the Cn would be the last element, and these are transposed. So with that in mind, we can find out what is the mu A given B, or Tn plus 1 given Tn equal to. So mu A is in our case, what is that? That is in fact the zero, because here we have a long zero vector, and mu A is in fact or actually mu B in our case is equal to the 0. So this is the last element entry. So as we are now dealing with something which is on the very bottom, we are expressing it with respect to this mu B and not mu A. So everywhere where there is A should be B, and where is B should be A. So this here is mu B is therefore 0 plus, and here we have sigma AB, which is, we can see here, the K transpose, because it's the sigma BA and sigma BB inverse. So not sigma BB inverse, but sigma AA inverse in our case, which will be Cn inverse. So we have the K transpose Cn inverse, and then times the xb minus mu b. So xb in our case is like the first part, which is the Tn, the entire vector T until capital N, and minus mu b is 0. So we have simply the Tn, the entire vector. But we omit here the Tn, only the T, and here these values are in fact already the real training data values and not the some random values generated, but the real target value which corresponds to our observations. So this is how we calculate our mean, and then for the sigma we calculated based on this formula. So sigma AA will be the sigma BB, which is in our case the C here, minus, so we have C minus, and then minus sigma AB, so which is sigma BA, which is K transpose, and then we have sigma BB inverse, so that's sigma AA inverse Cn inverse, and then AB transpose, so that is actually a sigma AB, and that is here the K. So we have now the formula for the mean and variance based on the conditional probability of this partitions of a multivariate or a multidimensional vector and its normal probability distribution. So this gives us the normal distribution, which no longer has as a mean the 0, but it has a mean which is governed by this target value vector. And just as a remark, in order to have the C, in this case positive definite, we need to have the K positive semi-definite. such that the beta, which is a positive value, will for each diagonal entry will give us, even if there would be previously 0, will add the beta inverse, and then it will, the C will be therefore positive definite. Also, in order to obtain our kernel, we can use also in this case any kernel construction techniques. Now here on the diagram you can see how this distribution, multivariate distribution of the T is represented here. So we can see that the covariance matrix makes it some ellipsoidal shape, this normal distribution. And here we have the T1 and we have T2 values, and these two values are simply given the probability of T2 given T1. We will see that here suddenly this T2 will have the probability distribution governed by this mean value here, and the variance is simply here expressed by this large spread. So we can see that even if the joint distribution has the mean 0, the conditional distribution doesn't have the mean in 0, as it is the case here. So from this we have devised this predictive distribution, but from a Gaussian process perspective rather than from the weight parameters perspective. So this is the key outcome. How do we calculate the predictive distribution of a given a training set Tn and Xn and the new value Xn plus 1? How do we calculate the mean and variance for our distribution, for our to find out the T which corresponds to X capital N plus 1. Based on the result, where we, through this trick of the conditional probability, have obtained the mean and variance for our new input vector X, we can also reformulate it. It's still having this nomenclature that the new input vector is X capital N plus 1, so the mean of X capital N plus 1, which we can also call it of like a Y of X, is has this form of the sum of AN multiplied by the KN of small n for each training input with Xn plus 1 with our new point, and then the AN in such a case will be the nth component of this C capital N inverse times the training target vector T. So this will result into a vector matrix vector multiplication will be a vector, and the AN will be the scalar, the nth component of that vector. Now, if the K, the kernel, depends on the distance between Xn and Xn plus 1, so the new X, then this kernel is actually will be a radial basis function if it only depends on the distance and doesn't have some other terms like we have seen this more complex kernel before. So this is a radial basis function, and when this kernel is distance based, as the radial basis function is, then the resulting Gaussian process predictor is a sum of radial bumps, one per training data point. So over each training data point, we have here one Gaussian blob, which is then influencing the our prediction of the value y in terms of both mean and also the variance. And we can see here that this predictive distribution which we have generated can be, in case our kernel is defined as a finite set of basis functions, we can either derive an equivalent kernel from this Gaussian process, which we can call the functional space viewpoint, where we have the probability distribution over the functions y, or we can obtain it as a predictive distribution by this Bayesian treatment by taking the parameter space viewpoint, where the parameters are the weights w. And let's compare these two approaches, the functional space viewpoint versus the parameter space viewpoint. So what is the computational complexity difference between these two? So we have seen that in the Gaussian process, the heavy computational operation is the inversion of the CN matrix, which is the ground matrix plus the noise precision on the diagonal. So inverting that one will lead to a inversion of an n times n matrix, because we have the CN matrix has n times n dimensions, and this leads to O(n) cubed complexity. And for the parameter space viewpoint, we have the basis function model. There we need to invert the matrix Sn, the posterior covariance, posterior probability of the weights matrix, covariance matrix, which is of m times m dimension, which the dimension m is the number of weights in the weight vector, or the number of features in the defining as the feature space, dimensions of the feature space. So this will lead to, as we also need to invert this matrix, this is the highest computational complexity here, this will lead to O(m) cubed complexity. But however, the m is typically often much smaller than n, so the number of feature dimensions is much less than the number of training points, and therefore this would the computational complexity will favor the basis function framework, the parameter space view. This is in preprocessing. In runtime, we have a vector multics multiplication, which is the highest complexity in this process, which will be of O(n) cubed complexity. And in the case of the parameter space viewpoint, we will have O(m) cubed complexity as the vector matrix multiplication, because here we have the design matrix times the t, which will be governing us this complexity. And therefore, we will see that also at runtime we will be favoring the parameter space viewpoint if the m is much smaller than the number of a number of n. This can be actually reduced in the Gaussian process in the way that we will reduce the amount of basis functions so that they do not sit over the entire training set, but this radial basis functions, but they will be only defined over some points, or they would be defined only in some within the somewhere within the input space, and they will not be therefore even above any training data points if we, for example, use the k-means clustering for defining those centers. So that could be done in taming the computational complexity of these kernel approaches. So performance-wise, we can see that the parameter space viewpoint is somehow more beneficial, but there is another benefit to this kernel methods, to this quotient process, and that's the following one. The benefit is that it is the quotient process for regression can have kernels which will correspond to an infinite dimensional feature space. So it will lead to that the kernel is actually a sum of feature transformations that are infinitely many such feature transformations, so leading that the feature space will be infinitely dimensional. Such a kernel can exist, and already the Gaussian radial basis function governed by this simple squared distance in the exponent is already such an example of a kernel which would correspond to infinite series expansion of the this of complex exponentials. So it will be even complex valued exponentials, which will be result of this decomposition of this kernel into this feature space. So what is the big deal about the infinite dimensional feature space? The feature space, the dimensionality of the feature space defines us how complex the actual model or flexible our regression function can be. And for example, with this kernel, our functions can be infinitely flexible. So the flexibility, for example, if we will have the parameter space with polynomial basis functions, maybe we have just a linear and constant component, and that will not lead to very flexible regression. Here we have infinitely dimensional, infinitely flexible functions, and that is certainly of a benefit. And sometimes we could say, well, if we have too high complexity, allowing that this might lead to overfitting. However, another benefit of our quotient process is that it has a built-in Bayesian framework where we have the prior of the distribution, probability distributions of the functions y, and we have also the likelihood, so that we have automatically regularized model. So this regularization will lead to the fact that the resulting functions will not be overfitted, but will be a smooth representation of our training set. So overall, this kernel approach is a dual approach to our parameter space viewpoint. And while it might lead to higher computational complexity, in some cases, it might have the benefit that we have an infinite dimensional flexibility, which is self-regularized. The prediction of quotient process is highly dependent on the covariance matrix Cn. This matrix has been obtained by the Gram matrix, which is composed of kernel functions of various input points or input vectors, and it also depends on the noise associated with the target variable. And this kernel and the noise, they in fact so the noise itself is a parameter, and the kernel sometimes have certain parameters which can be tuned, and that will influence how this covariance matrix will look like, and it will also influence the predictive power of our model. So we might want to define the parameters pointwise and choose hyperparameters pointwise and choose them such that the predictive outcome is the best. For that, what we would typically be using in as often used in the parametric viewpoint would be the maximal likelihood estimation, but in this case we are not dealing with like weights, but we are dealing with the hyperparameters. So if we will be dealing with the parameter viewpoint using weights, we would need to first integrate out the weights, and then we will have this marginal distribution, and in the marginal distribution we will be performing this maximum likelihood procedure, which is therefore called a type 2 maximum likelihood, or also empirical bias or evidence maximization. So in fact, we have here this likelihood function pt given theta, where the theta are the hyperparameters, and for example, such as the length scale, which we have here, and or the noise precision, which we have here, and this likelihood function, in fact, it is the model evidence. As we can see, this will be the PT that is the denominator, but it is defined through these hyperparameters. So let's perform the maximum likelihood estimation of this model. So this is a multivariate Gaussian, and therefore we can perform the logarithm, and we want to maximize this logarithm with respect to certain hyperparameters, or its overall value, by changing these hyperparameters. So the logarithm leads to the form where we have here one term which is dependent on our covariance matrix, then another term which is dependent on the covariance matrix which the hyperparameters are contained in, and also we have here the target values from our training set, and then we have the third term, which here is just a constant, and we cannot change that term by changing the hyperparameters. Well, if we then perform the partial derivative of this log likelihood, then the first term, the ln Cn, will lead in fact to the derivative, which is the trace of Cn inverse, so the covariance matrix inverse, times the partial derivative of Cn with respect to the particular hyperparameter we are interested in. And so this is achieved through a chain rule. And then we can look at the second term here. The second term here we can reformulate slightly such that we express it as a trace, and this trace we can have the partial derivative with of the Cn with respect to the Cn inverse with respect to theta here in the middle, and then when we are reorganizing the terms or the entries of the trace product, then we can see that we can express here this derivative of the Cn inverse as the minus Cn inverse, or powered by -1 divided divided by theta I times the Cn inverse, and then the outer product of T. Well, that can be further reformulated as a not as a trace again, and where we have the similar structure as we had before here, but now we have the minus T transpose, and then the central term, which was previously the Cn inverse, and it was derived as this structure times T. So now the final form of our derivative is of our log likelihood is the one term with a trace, and the other term which we just have derived. And we still have these partial derivatives of the Cn with respect to particular hyperparameter. So we can think of like which hyperparameter we want to perform the optimization with respect to which one, or we can do it jointly as a vector of hyperparameters, and then the gradient function for each hyperparameter component will have slightly different structure, because, for example, the partial derivative of the covariance matrix with respect to beta, with the noise precision, will lead to the so here we are having only the component where the beta is from our covariance matrix, and therefore as a separate sum here. So therefore the result will be the standard derivative of this scalar times the matrix, the identity matrix. So where it was powered by -1, now it's powered by -2, and -1 goes into the front. So this is one partial derivative. And if we would like to perform the gradient descent in order to find the minimal negative log likelihood, for example, and then or the maximal log likelihood, then we will be using this term here in this as this term in the trace, and this term here in this other term, and so this is for the hyperparameter characterizing the noise precision. And if we are interested in the hyperparameter which is called the length scale, or actually just the variance of our in our kernel, then we can perform this partial derivative of the Cn with respect to this parameter, and that is in fact we have here the Kn, so that's the kernel gram matrix partial derivative with respect to this hyperparameter, which leads to this function, which is in fact for every m or n from 1 to n. So this is for all the entries of our matrix. So this is a form how we write it, the matrix form. So this term will be then used as each element in the matrix. We will have to calculate this derivative. So once we have that, we can put that derivative here, and here we will have therefore these matrix multiplications, which will give us the gradient this time for the change in the length scale hyperparameter, and we can perform an iterative optimization loop with the gradient descent, sequential gradient descent, in order to find these hyperparameters, which we can then use as point-wise estimates in our model. So as I said, we will be using the gradient as the component in this gradient descent non-linear optimization loop, and because the ln of the likelihood function is in general a non-convex function with multiple maxima. We can, instead of just working with MLE of the type 2, we can also perform maximum a posteriori estimation in case we have a certain prior of the of our probability distribution over our hyperparameters. So in that case, the estimation is straightforward. We just want to find the maximal value of the log likelihood plus the log prior, and we can do it in a similar way that we are here performing the derivative as well in order to find the gradient descent step towards a better hyperparameter estimate, which fits better the data overall. And then we can also, although this is actually not tractable, but we could also set up a fully Bayesian treatment and evaluate the marginals over theta weighted by the product of the prior and the likelihood. So here we can obtain the marginal distribution of t over all possible hyperparameters, and that could be leading to a as a predictive distribution where the uncertainty of the hyperparameter setting will be integrated into the prediction of t. However, this is intractable, and we will need to resort to approximations. One more aspect which is interesting to shortly discuss is to discuss a case where the hyperparameter itself is dependent on the input. So, for example, we have this so-called heteroscedastic case where we have input-dependent noise. So the beta, the precision of the noise, is dependent on x. We can imagine that we have a phenomenon where for larger values of input, we will have slightly maybe different characterization of the noise than for smaller values of the input. And therefore, we can extend our target function t of x is not only the y of x plus epsilon plus noise, so the regression function plus the epsilon, but the epsilon itself is a function of x, and it's governed by the probability distribution of some of beta precision, which is a function of x, and it has zero mean, let's say. So therefore, we can in fact set up two Gaussian processes, one for the to characterize the probability distribution of y as a Gaussian process, where we have the zero mean and we have the covariance matrix characterized through the kernels and also through the hyperparameters within these kernels. And then we have the separate Gaussian process for the noise precision function, which is, we can call it g of x here, because we definitely want to achieve that beta is a positive quantity, so the variance cannot be a negative quantity, and we can achieve it by setting the ln beta to become a function gx, which is unconstrained, so that one can be of any value on the real axis, and we can see that if we want to then express beta, it will be the exponential function of gx, meaning that the beta will be always positive. So we already have done this kind of trick here, and therefore we are looking at the quotient process characterizing the log of the noise precision, which is this random probability distribution G, which is modeled as the quotient process with again a zero mean, and as a quotient process it also has some kernel function or the gram matrix, which is having some characterization between the input values x, and it also has some hyperparameters which are characterizing this noise function. So, and then if we want to in this case learn the hyperparameters, what we can we end up with is that we have one likelihood function, which is for the t characterizing the target value. N is the probability given yn and g xn. So these are the inputs of the training set, and this is the output target outcome from the training set. And here we can replace this gn by the beta, which is governing our normal distribution of the Tn. So this is the normal distribution with this covariance or variance. And that is in fact equal to the normal distribution with the mean of y, and the variance is characterized by this exponential function of a negative g, because beta x inverse, so the variance is exponential of minus g. And therefore we have now the likelihood function, and we also need to formulate the prior. The prior is of these two random variables y and g, as we consider them independent. Therefore, each of them are governed by a normal distribution with their separate gram matrices. And as we are treating here the g for all the input variables, for all the input variables x as with a joint probability. Now, our likelihood function over all input data will be therefore a product of this normal distribution, which we have obtained here. And once we have the likelihood and we have the prior, we can integrate out the y and g, and in order to obtain the likelihood for performing the MLE of the second type. So here we are integrating the y and g with in the integral to obtain the marginal distribution of t, where we could then express with the fixed parameters of hyperparameters associated with the both y and g. And then we could use, once we have this likelihood function, then we can perform our derivative of this log of this likelihood function in order to perform the gradient descent. However, this non-conjugate form of this e powered by minus gx leads to a non-Gaussian posterior, which unfortunately will need to again make use of a certain approximation of this PT likelihood. So this is just a comment on how this learning of hyperparameters can be done in case we have not only the y is the function of x, but also the noise itself is a function of x. In the context of learning hyperparameters, it is worth mentioning the technique which carries the name automatic relevance determination. So here we are just extending this hyperparameter learning process, which we have discussed on the previous slides, for each input variable dimension. So imagine that we have a kernel, which is an exponential kernel, which has now a so-called ARD parameter, the automatic relevance determination parameter eta, and it is defined for each input dimension. So here we can see that we have the xi. Here we have a two-dimensional case where the I will have value 1 or 2, and we have this kernel, which has basically this is defining us what will be the precision of each of along each dimension, or what will be the reciprocal of the variance. Now we can see the result of varying this parameter in the following two plots, where in one plot we can see the resulting prior over function y, just one function. We have seen these samples drawn from the probability distribution with respect to y in a one-dimensional case before. Now this is a two-dimensional case, therefore instead of a curve we have here this surface, and we can see that for one value of setting of these eta parameters, namely for each dimension the eta is equal to 1, we see that it forms somehow in both dimensions similar, has a similar behavior. Now we change the the eta parameter eta 2 to 0.01, and we can see that while for in one dimension, x1 dimension, we will have the function y, the prior, behaving in the same way as before. In the other dimension, we can see that the function is largely independent of the changes along the or not independent, but it's not very sensitive to the changes in the variable x2. So we can see obviously how these changes are happening, but now we will be considering it from the perspective of how relevant each dimension is. Because for the regression problem, we have the input vector, but some elements of this input vector might be more relevant than the other, and this automatic relevance determination as a part of this hyperparameter tuning strategy will be highlighting those dimensions which are more relevant than the others. So each dimension impacts the regression task in a different way, and our hyperparameters can be tuned to the importance of each dimension of x. So let's see this on one particular example. So we have generated a three-dimensional input here, which is consisting of x1, x2, and x3 components. And so forming this input vector x. But we have generated our target variable from the x1, where the t is equal to sinus of the 2 pi x1 plus some quotient noise. And then we took the values of x1 and we added the quotient noise to the x1, forming the second dimension x2. So we can talk about a noisy input for the case of the x2 dimension, and then for the x3 we have just randomly generated the x3. So it means that this will lead to the fact that x1 will be a good predictor for t, the x2 will be a noisy predictor for t, and the x3 has only chance correlations with t. And then we will be performing our hyperparameter learning for each dimension separately. And we can see that the hyperparameter learning for the eta 1 will lead to a relatively high value on this logarithm scale. Then this x2 dimension, so corresponding eta 2 will be somehow comparably much smaller, will be converging to a comparably much smaller value because it's relevant but not that relevant for the regression task for the target values of t. And then we have the third component x3, which is becoming the eta 3 will be having a very, very small value around 0.001, expressing that we tuned this hyperparameter such that this third dimension is of no relevance. And this can be also used for strategies of reduction. So we can reduce the complexity of our model by simply reducing certain dimensions from our input vector and not considering them in our model. So this was the example of the automatic relevance determination as a part of this broader category of hyperparameter learning, which we have discussed before, and it was extending this notion by having the hyperparameter learning for each input variable dimension separately. In a probabilistic approach to classification, we formulate the result as a posterior distribution, P t given x, and the probability is in the range between 0 and 1. Now, in our Gaussian processes, we have been dealing so far with regression, and now we will see how can we use the Gaussian processes for the classification tasks. However, the Gaussian processes are making predictions in R. So you will receive an prediction which is some real value, and it is not bounded on the interval of 0 and 1. This is similar to the regression case we had for linear models or for the neural networks for that matter. However, now, similarly, we can apply a nonlinear activation function as to this argument of the Gaussian process, and this nonlinear activation function, like the sigmoid, will then transfer or remap our A, in this case, into a interval 0 and 1. So we will perform the Gaussian process on the probability distribution of AX, which will be in some sense equivalent to what we did for regression for the TX. And in that sense, we will be also we will be also inheriting the prior from the weights as we have done previously in the case of the regression conceptually, but we will not have these weights explicitly present either in this case. However, the situation overall will be much more complicated, in fact, because we will have here this nonlinear activation function, which will make the classification task overall a little bit more complex than the regression. So we start with the training set, which is a coupled X and T sets, X1 to X capital N and T1 to Tn. So X would be some input vectors and T will be a value between 0 and 1. Actually, it will be either 0 and 1 for the training set, so that would be either zeros or it would be ones, and it will be for this two-class classification task, which we will be looking at in this context now. We will name the test point, the new point we are interested in to find out in which class it is, in class 1 or class 2. We will call it X capital N plus 1, and it will have the corresponding target value, which will be after the Tn plus 1. And we know why we are calling it this way already, because we will somehow add it to this vector xn as one of these inputs, or the Tn as one of these outputs, in order to express this as a conditional probability of this Gaussian process. So that's exactly our goal. We would like to know the predictive distribution of probability of Tn plus 1 given the training set Tn. And of course also xn and some hyperparameters which our kernel, for example, will be associated with. So let's get to it. Let's try to find now this predictive distribution Tn plus 1 given the vector Tn. So first we will introduce the prior, the Gaussian process prior over the vector an plus 1. So these are all these, I would call it here in this context, activations, which are the arguments then for the sigmoid, which here is a vector of all these ax1 to ax capital N, and the probability of this will be a Gaussian process prior. Therefore, the probability will be a Gaussian with a mean at 0, and the covariance matrix will be already now this matrix we are familiar with, Cn plus 1. So this covariance matrix, in this case, it naturally should not really include noise, because we assume that our labels are noise-free. Everything has been correctly labeled in the training set. However, for convenience and to secure the positive definiteness, we will define this covariance matrix in the more or less the same way as we did it for the regression task. So we have our kernel part here also associated with the two pair of the training input points and the hyperparameters, and then this noise-like term nu, which will not really represent a noise, but it will be there as a small fixed value, which will be, as we can see through this Kronecker delta, only on the diagonal. And then the Gaussian process, which is a Gaussian probability distribution, as we know, defines actually a non-Gaussian process over Tn plus 1. And the non-Gaussian process is because we have here the sigmoid, which is a nonlinear activation, and that sigmoid will cause us that we will not be dealing with the Gaussian anymore, but some other probability distribution. So the predictive distribution, which we are looking for, can be obtained by conditioning by conditional probability of Tn plus 1 given Tn, as we said, and we can express this for Tn plus 1 equals 1. What is the probability given the training set? And then we will get some probability value. And as we have a two-class classification scenario, then the other possible probability will be the Tn plus 1 equals 0, and that will be simply 1 minus probability Tn plus 1 equals 1 given Tn. So it's enough to express this value, and from this value we can already infer the probability that it belongs to the other class. And here we can see, for example, as we have seen previously, this Gaussian process prior can generate us some functions given the kernels which we are defining over the input points, input vectors, and this prior, as we can see here, is changing values between 10 down to -5, almost here is -5, and so on. So, and this is an argument into our sigmoid, and we can see what the sigmoid would do with this one sample function ax here. So this sample function ax will be now the sigmoid sigma x or sigma ax actually, and we see that here when we have a large positive value it will be almost 1, and then once we are going negative, so we are crossing 0, we will go towards we will be at 0.5, and then at this minimum we will have much more pronounced dip in a way on this scale, however. So we will go almost to 0, and then again we will have a higher value, 5, so we will go almost to 1, and then again to 0 for -5, and so on. So we can see that the characteristics of this function, the minima and maxima, are much more pronounced through the sigmoid and giving us the membership of the particular point to a particular class. Class 1 for when it's close to 1, and class 2 when it's close to 0. So now we want to find out this predictive distribution. And in fact, this predictive distribution can be expressed as the conditional probability of T1 with respect to a and Tn plus 1 with respect to a n plus 1. And this, in fact, is just the activation function, which is the sigmoid. So this is here. So P Tn plus 1 equals 1 given an plus 1 is the sigmoid, and times the probability of an plus 1 given Tn. So this is our posterior of an plus 1 with respect to the training set, and we would need to evaluate this function in order to be able to solve this integral. This integral is not as easy to solve, or in fact it is intractable with the sigmoid, but we have already seen previously in the case of classification that we can approximate the sigmoid with the probit or inverse probit function, and then given that with the probit we can perform the integral, because in fact the probit is an integral of Gaussian. So therefore, if we would know this probability distribution, so this second term here in this integral, in such a case, we will be able to use what we already have learned, that this integral, sigmoid times a Gaussian distribution in an integral is equal to a sigmoid with this term where we have the mean of the Gaussian distribution in the numerator, and then a square root of 1 plus pi sigma squared variance parameter of the Gaussian distribution divided by 8. So this is the argument now for the sigmoid, which is an approximation, but pretty close approximation based on the similarity between the probit function and the sigmoid function. So but we do not have this function or this probability distribution readily available, and therefore we will need to approximate it with the Gaussian through the Laplace approximation. So we might remember the Laplace approximation basically is an approach where we want to find out what is the mean and what is the variance or covariance matrix of our distribution, and that will be then parameters for the Gaussian, which is approximating that otherwise more complex distribution. So let's see how can we get to this probability distribution of an plus 1 given Tn. So that function is in fact equal to an integral of p an plus 1 an given Tn dan. So here we can see that we have like a joint probability, joint conditional probability expressed, and what is happening here, we are marginalizing and integrating out the an. So, and after we will be integrating it out, it will be out. It will no longer be in this probability distribution. So that's what we are doing here. That's why we have represented this probability distribution with this apparently a more complex form. Now, this can be reformulated in a way that we can see this as a posterior, and this posterior is composed of prior and a likelihood function and then normalized. So let's see that this posterior here is can be seen that it's a product of the prior, so this joint distribution an plus 1 and an, so that's the prior, and the likelihood is Tn given an plus 1 an. And we know that this posterior is proportional to this product, but it's not equal. That's why we need to normalize it, and that's the normalization term will be p Tn. So, and as it is not, the Tn is not expressed through and we can take it because it's a training set classifications, we can take it out of the integral. Now the next step is to realize that the Ptn given an plus 1 an is in fact, which is written here, Ptn n plus 1 an is equal to Ptn an. This means that an plus 1 is actually doesn't change anything on this probability because the Tn is completely described by the an. It's this sigmoids really, so which are associated each n small n with a t and small n in this case. So individual training elements. So we have now here, we can replace this probability with this probability, as we can see it has been replaced here. And now we see that in fact this, what we have called as a prior, it's in fact a joint distribution, and we can represent the joint distribution by a conditional distribution times the marginal distribution. So PAN plus 1 given AN times PAN is giving us this joint distribution. So we can reformulate it in this form, and then and we have removed this A capital N plus 1 from this conditioning. And finally, we can see that we can actually express this term here as a joint probability T and AN. So we have taken this marginalization from this joint probability, but this term actually is appearing for calculation of this joint probability. So we have joint probability PAN, TN, and then if we divide by the Tn, we will get from the joint probability the conditional probability. So we end up in product of two terms, probability of AN plus 1 given AN, and then probability of AN given TN, DAN. So now we have reformulated this term here, which we are looking for because we need it for calculation of this predictive distribution, into an integral of terms which we can perhaps already be able to find out what they are. So for example, we can see that the PAN plus 1 given AN is the same as we had before the PTN plus 1 given Tn, when we had the conditional distribution expressed as a predictive distribution for the regression. And the result there, except that now we have A and before it was T, was that it was a normal distribution of AN plus 1, so the Tn result given the mean, which was as we were characterizing this partitioning of this C capital N plus 1 matrix, the covariance matrix, that could be partitioned into the Cn and then the K and K transpose, and in the bottom right it was the C. So, and we can use that for expressing our mean. So this mean is also coming from this input, the A capital N, and the covariance matrix is actually variance, because we are really having here just one outcome value, is C minus, and then we have essentially everything the same for this variance. The only change here, which we have with respect to the previous case of the Tn, was this that we have here AN instead. So this is already good, because we can see that this probability distribution is a Gaussian. So that's nice. Now we have to find what should we do with this term here. So this term here, as in the way between AN and Tn is a nonlinearity of the sigmoid, this probably will not be a Gaussian function. So, however, we can find a Laplace approximation for this posterior A capital N given T capital N, these vectors, and we can then use the standard result for convolution of two Gaussians. So if we can represent this as a Gaussian, then we can solve this integral, and with that we can solve this probability distribution, and then we will have achieved our goal of being able to solve this predictive distribution. So let's do that step by step. Now, if we want to perform this Laplace approximation, we need to find the mode of this distribution, and we need to find the variance. And the or covariance matrix, and this can be obtained by the Hessian of this probability distribution at the mode. So we need to find the mode and then the Hessian matrix, and then we have our approximation of this probability distribution given by a normal distribution. So let's have a look how this can be calculated in principle. So this is equal to the marginal distribution PAN, and this is the PAN is a Gaussian process, and as a prior, it's a normal distribution with the zero mean and with the Cn as a matrix representing our covariance matrix. Then, so that is our PAN, and the likelihood here is the likelihood is simply the relationship between like Tn given An. It's a function, it's a sigmoid function, and therefore we express it, this probability, as each of these points in the An is independently, underlying is independently drawn input x. So we can find this probability as the product over all of these individual probabilities for all the input samples. And that is our cross entropy representation, or not cross entropy representation, that would be the error, but this is our representation of the sigmoid, the Bernoulli distribution, in fact, where we have the sigmoid here times the which is either 1 if the Tn is 1, or it is 0 if the Tn is 0. Then in that case this will be 1, and then this other term will be kind of switched on, and if the Tn is 0, then this will be 1 minus 0. That's why this term will be switched on. So it's this, and with this we are basically multiplying the probability of the Tn given An. And that can be, in fact, reformulated into slightly different form, which we can observe here. One trick which we are using here is that 1 minus sigmoid of An is sigmoid of minus An. So, and once we have that, we can represent this as sigmoid of minus An, and this exponent here we can split into two. One will be representing the 1, and one will be representing the minus Tn. So I will now just take this product of this part and the product of this of minus Tn, and that is actually written here. So we have the sigmoid An powered by Tn and sigmoid of minus An, which is representing really what is here inside, powered by minus Tn. And we can express what is the sigmoid because we know what is its functional value. And sigmoid is for sigmoid An is equal to 1 divided by 1 plus e powered by minus An. So this part, this denominator part, is coming from this sigmoid, and then this part, as it is, as it here is, as here it's minus in this exponent, so we put it under the same exponent. We have to perform a reciprocal of this, so this will, instead of going into the denominator, goes to the numerator. And then, just to simplify this expression, we multiply both numerator and denominator by an e powered by An. And that means here, if we, in the denominator, times this will be equal to 1, and times 1, it will be equal to e powered by An. So we will have here 1 plus e powered by An plus 1. And that is the same thing as we have here. So we can actually cancel that out. And what we will then end up with is, so we have here this reformulation. So we can cancel these two out. And we end up with e powered by an and that powered by tn. And that is the result here. So actually these two terms, except of this powered by 1, is equal to e powered by a and tn, and then we have to add this 1 times sigmoid minus n here, and this is now our product. So this will be our current representation of this likelihood function, and we are therefore solving this probability likelihood is expressed by this product of where there are inside these two terms. Now we use both this likelihood and the prior in our search for the maximum a posteriori, which will be at the mode of our Laplace approximation. So therefore we will be performing the maximum log likelihood. So we will perform logarithm of this function. Actually, we will perform the logarithm of this function because they are proportional, and the mode of this and this product is at the same location, and that's what we are interested in. So we are now performing the search for the an star, we can say, which will be the mode of this conditional probability distribution an given Tn. So therefore we need to perform the logarithm, and the logarithm will be performed of this normal distribution, this multivariate normal distribution, and from this this term, this product term here. Let's do it. For the maximum a posteriori estimation of the PAN given Tn, and here is the what is it proportional to these two terms of the prior and the likelihood, and here therefore we have the prior, which is the normal distribution, and the normal distribution has this, after the logarithm has this part coming from the exponent, and then we have two constants terms, which is this one term and this another term. Constant terms with respect to the an, because we will be also then interested in the we are trying to maximize this probability, trying to find its maximum of this probability, and for that we will be searching for terms where the an is, and where the an isn't, we cannot actually change their contribution to the probability anyways. So and this is the one part, this is the prior. The likelihood, the logarithm of the likelihood is now, instead of product, we have the sum, and what was in the exponent of the e, we have now the a and tn is now just two multipliers, and then we have this other term ln of 1 divided by 1 plus e powered by an, which is simply we are putting the sigmoid into the logarithm, and so this argument should be normally in the bottom in the denominator, but it is now taken into the kind of numerator because we have here this minus sign. So but it is essentially expressing us the sigmoid function. And then further on, we can see that this term we can take out from the sum this dot product. So this will be basically individual components forming the dot products. So we can take that out, this dot product of these two vectors, and then we have just this term of the sum of the logarithm of 1 plus e powered by an. Finally, we will give this logarithm of the posterior log posterior, we will give it this function name now, and we collect all the terms from both the prior and the likelihood together, so that we have this one complete function representing all these terms after the logarithm has been performed. Now we will be attempting to maximize this logarithm, which contains both prior and likelihood, and therefore it is the maximum a posteriori estimation. So as once again, we are searching for the maximum a posteriori estimation of this PAN given Tn, and then we have this representation of this log posterior here, which is represented by this psi, capital Psi. However, we can also see it in a way that we have just those components which contain an, and the rest is the constants, and this view will give us clear view on these three terms, which we can perform the derivative of partial derivative with respect to an. So we can see here that in this sum we have this logarithm term, and if we perform the logarithm of this term is that is the derivative of the logarithm of this term, and that is equal to the logarithm itself. So this will be therefore 1 divided by the argument in the logarithm, so 1 divided by 1 plus e powered by an, and then the inside of the logarithm, this term will be we will perform the logarithm, and that is the e powered by an. Now that is equal to, in fact, that is equal to, if we divide by the e powered by an, then this entire ratio, we will have here 1 in the numerator, and this will be e powered by minus an instead of this one, and this will be equal to 1, and that is equal to the sigmoid an, in fact, and we can put, as it is the sum of these individual components, we will create the vector. This will correspond to a vector of the sigmoids, of the sigmoid results. So that is maybe the most was the most complicated term. So now we express the gradient of this log posterior, this the gradient of C is equal to minus Cn inverse, so that we have from here, we have the an transpose an. If we perform the derivative of this square term here, we will end up just with 1 an, and this 1/2 will be also cancelled out, because it will be 2 times an, so we will lose this constant here. It will be cancelled out, so that this term, then the derivative of this term will be simply Tn, and then derivative of this term will be simply the vector sigmoid n. And now also we want to perform, so this is a derivative, and with this derivative we need for, in fact, for performing an iterative reweighted least squares, which will lead us to gradually finding our maximal value for this log posterior, and that will be corresponding to gradually finding what is the an, what is the mode at of this probability distribution. And then we also need the second order derivative, the Hessian matrix, in fact, and that is of this log posterior, and that we calculate from the first order derivative. And here we can see that from this term it is easy to find what is the second order derivative, so that's only this minus Cn powered by -1, and then the Tn will be there is no an, therefore it will become 0, and then this term will be in fact represented as a vector, and with respect to derivative of vector with respect to another vector, and we have that here where we have the partial derivative of one vector with respect to another vector sigmoid n divided by with respect to an, and in fact that will lead to a diagonal matrix which will have simply the derivatives of sigmoid in the diagonal entries, and it is expressed here. So this will be an n times n matrix, and on the diagonal there will be terms of sigmoid an 1 minus sigmoid an, and of the diagonal it will be zeros, and that is expressed again by this Kronecker delta term, which is 1 if the n is equal to m, and otherwise it is 0. So, and this matrix, which we will generate through this second order partial derivative, we will call a Wn. And so therefore the second order derivative with respect to this term, or first order derivative, then will be this minus Wn matrix. So this is our Hessian matrix, which we can see that this Hessian matrix will be consisting of a negative term, or we can say actually that the Hessian matrix is negative of that, and there are some discussions of what is really the Hessian matrix. For the discussion of the Bishop formulation, we will denote the Hessian matrix as the negative of the second order derivative, and that is this matrix. We claim that it is positive definite, and it is positive definite because this function, this matrix needs to be negative definite, and we can see that it will have this is a Cn is by construction, by definition, is positive definite. Its inverse is positive definite, and its minus makes it negative definite. So it's for sure negative definite. And then this matrix is does it have as components? It has zeros, and then it has these terms in the diagonal, and these terms are sigmoids, and multiplication of two sigmoids, it's a positive number definitely, and it will be something between 0 and 0.25. Just imagine that if this is 0.5 and this is 1 minus 0.5, this will be maximum 0.25. So these therefore will have positive entries on the diagonal. So it will be, and with minus it will have, therefore will be subtracting those entries. So this matrix itself will be negative definite, and the negative of it will be the Hessian matrix, and that's why it will be positive definite. So the log posterior, it will be strictly concave. So if this matrix is strictly positive definite, which it is, the log posterior will be strictly concave. So you can imagine that the function always, when it sort of grows, it bends a little bit down, and it bends down everywhere, so that that means that it has a single mode, and that is the global maximum. So this probability distribution, or this log of this posterior probability distribution, has just one mode, and it has just one maximum. That's great, and now we simply need to find it. And now we already have, for our iterative reweighted least squares, we have the second order derivative, we have also the first order derivative. So in fact, this is more or less everything what we need for our iterative process of finding the mode of this probability distribution. So these iteratively weighted least squares are, I'm just rewriting what we had before when we were introducing it in the context of classification, and there we were dealing with weights. So we are not dealing with weights now, but just that you see how we were calculating it. The new weights were calculated from the old weights minus the Hessian inverse times the gradient of the error. So we will do the same thing here, but not with the weights, but with the Hessian and with the gradient and with our an variable. So that means that here we just rewrite from the previous slide what is the gradient, and we see here what is the Hessian. Here the Hessian is minus of this, so we are interested in this term, which is this term here, the negative definite matrix. And now we can simply start formulating our iteratively weighted least squares. We need to perform this iteratively weighted least squares because we have the an as a part of these functions. Like, for example, we have it as a function of this sigmoid here, and that's why we need to perform our iterative process, and we cannot simply have a closed form solution. So the a n in the new one is equal to the a n old one plus the, and here we have this Hessian matrix powered by -1, and then we have the gradient as exactly as it is described here. So, and then we have here again we are putting in the values what are the corresponding second and first order derivatives. So this is the second order derivative, the minus of the second order derivative, and this is the gradient which we have expressed here. So we just put it in here, and then in fact we can put the an into this expression by multiplying it with Cn with basically this term inverse and with the inverse of this term here, and therefore we can see that the an is here multiplied with this term, because this term times this term will be identity matrix. So and we did it because we are having the same term here. So we are simply putting the an into this expression and putting this negative Hessian in the front. And then we have here the rest, which is the gradient, and we can further reformulate that into just this first part. Can be also reformulated by taking out the Cn, and therefore we will have here this identity matrix, and then we have here the W and Cn, which will then be cancelled out because it's an inverse here, as we can see. So and then we have here a slightly different term here, because we have now multiplied out this an with the Cn inverse and with the Wn, and Cn inverse plus and minus will cancel itself out, and then we therefore will have the an only associated with this derivative of sigmoid matrix. So the final function for these updates within our loop of iteratively weighted least squares will be guided by this formula here, which is the same as in the book. And at some point, we will find our maximum of this probability distribution, and that will also have a characteristic that the first order derivative, this gradient, in fact, will be equal to this term as we have it here, and at the same time it will be equal to, and this term will be equal to 0, because at the mode, at the maximum, this gradient will be equal to 0, and that leads to the fact that the an will be equal to the C capital N and Tn minus sigmoid n. So this will be a useful check whether this in fact is we are reaching that value once we are at the mode of an. And once we have completed our iterative process and we have converged to the mode, then we finally can say that we have obtained our Laplace approximation with having the which is then the normal distribution with the mode, or actually the mean value will be the an star, which came out from this iterative process, and then at that location we will evaluate the Hessian matrix, and that Hessian matrix inverse will be the covariance matrix. So finally, after quite a long time, we have finally obtained our posterior probability distribution approximation. This probability distribution is now approximated by this approximation distribution Q. At this point, we have finally obtained the distribution of an with respect to given Tn, which we approximated by the Qn, which is the normal distribution with the An star, the maximum a posteriori estimate as the mean, and our variance or covariance matrix is this term, and then we have the conditional distribution an plus 1 given an, which we obtained the same result as before in the regression, where the an plus 1 is normally distributed with the mean k transpose Cn inverse times an, and the variance, so this is a scalar mean in this case, and this will be also a variance, which is C minus k transpose Cn inverse k. So these two distributions are necessary for solving this integral. Now we know them, and now we can again apply these rules which we have obtained from the chapter 2 probability distributions on how to solve this convolution of these two quotients, and obtain therefore this probability of an given Tn. So the activation given the training set. Well, let's follow the steps as we were used to. So the px here is the marginal distribution, and that would be the first distribution in our case, and the conditional distribution with the linearly transformed mean of the first distribution will be the second distribution. So then we simply look at what is the expectation of y, which we are looking for. So we are looking for this distribution. So E y will be therefore the a mu plus b. So mu is in our case A n star, and then A is obtained from observing this mean here. So this is A mu plus B, so B is 0. So in fact, our A mu will be, this will be A, K transpose C n inverse, and times the mu, which will be A n star. So we solved this expectation. However, this A n star we can reformulate into being at the mode equal to Cn Tn minus sigma n, and in that case the Cn inverse and Cn will cancel out, and we will have a relatively compact representation here of K transpose Tn minus sigma n. Now, for the variance, we will have the formulation of so L inverse. So L inverse is, we are here in the conditional probability distribution. So this is L inverse. So C minus K transpose Cn inverse K. And then we have here A capital lambda inverse A transpose. So that is A capital lambda transpose, so that is here, sorry, capital lambda inverse is here, and A transpose. So these are the results, and in order to bring them to those which are also listed in the book for the variance, we would need to perform several operations, further operations, which we will show on the next slide. We are showing here that this formulation, which we have just mentioned, is equal to this formulation. So that's the first part, and then we just make one small change, and that is that we change our formulation of this A matrix from the previous slide, which was K transpose Cn inverse, and that is equal to in fact Cn inverse K and the whole thing transpose. And why is that the case? Well, because Cn matrix is a symmetric matrix, so its inverse is equal to itself, and the same holds for its inverse, and therefore this term will be equal to this term. So we just made a very small change here. Now, once we have obtained this, we are making a small change of variables, so where we say that C is equal to Cn inverse K, and K is therefore equal to Cnz, which is this, Z is this new variable, and therefore the K transpose Cn inverse K is equal to, which is coming from, which is this term here, is in fact Cnz transpose Cn inverse Cnz, which seems more complicated, but in fact it can be simplified because we do here this transpose. So we have C transpose and then Cn transpose, but also which is equal to Cn, and that cancels out with this inverse here, and we will be left out with Z transpose Cnz. And then for the second term, which is here, we will have the Cn inverse K transpose is actually replaced by this term, which is in fact the Z, and or now with transpose is Z transpose, and then we have this term and again Z. So we have Z transpose Cn inverse plus Wn inverse and times C. Now we did this change so that we can we reformulate it in this way, and we can see that now as we are multiplying with C this term from both sides, and the same holds here, we can put in fact the middle terms together, and we will obtain this result. So in fact, now we have the C minus, which was previously this term, we have now C plus Z transpose, this entire term, then C. And that is equal to a new term, which is minus Cn times, and here we have Wn inverse plus Cn, the whole inverse times Cn. So this is a little bit non-intuitive how we got from this formulation. Please note that here we are having the Cn inverse, while in the next bracket we have the Wn inverse. So, and this we will see on the following formulation here. So let's imagine that we are multiplying this term, which we have here in the bracket, by the Cn inverse plus Wn. So in fact, with the inverse of this term, we will obtain, what we will obtain is that we will multiply this first term with that term, and for the second term we will have identity. So so this first term will be Cn times Cn inverse plus Wn, and this term here will therefore form a minus identity, and we will be then having another term minus Cnwn. And now we have minus identity minus Cnwn plus identity. So in total, we have the result of this multiplication here, minus Cnwn. Now we perform. So this is just we were multiplying this with some term, and now we claim that this is equal to this, and this term we will also multiply, therefore, with the same term as we multiplied this term here. And what we obtain? What we will obtain that, because now we can see that it's not very clear, this is not an inverse of this, and they are also not next to each other. But now let's multiply this term, and we will see what we obtain. So here, our explanation might be a little bit convoluted, but let's go ahead. So this first part, we simply keep as it is. We simply multiply this together, and that will be that Cn and Cn inverse is in fact identity, and then we have Cn times Wn is the next term. And now, before we conclude with this term, with this statement, let's have a look if we multiply these two terms here with the inverse of this term. What do we obtain? We obtain identity times this term, and we can see also that if we are now taking out from this formula the Wn outside, so like we would be taking it outside. So here from this identity we will have, if the identity is expressed as Wn inverse times Wn plus Cn Wn, so we will have then Wn inverse plus Cn Wn. So once again, this term is equal to this term, and therefore this term here, these two terms, are equal to Wn, which means these two terms we have here, therefore they are equal to Wn, therefore C minus Cn times Wn is the result of this multiplication. Once again, in this case we have this term here multiplied with the term Cn inverse plus Wn exactly in the same way as we did on the top. So this apparently different term, after multiplied with this term, is minus Cn and this term times multiplied with the same thing is also minus Cn, therefore this term and this term have to be the same, and therefore we are replacing the minus Cn plus Cn inverse plus Wn inverse with term here, which is minus Cn Wn inverse plus Cn inverse times Cn. And now, at this point, we notice that we are still having this substitute variables z, and now we put back the what is equal to z, which is the Cn inverse times k, and then in that case we will have here a Cn inverse times k transpose, and therefore we will have this Cn cancelled out with the Cn inverse, and we will have k transpose, and then minus here, and then we will have for the second part also the Cn and then times Cn inverse k, so which will also simplify to k. So therefore we will have this final formulation exactly as it is written in the book, that the variance of the conditional probability of an plus 1 given Tn, or actually this predictive probability of an plus 1 Tn is having the variance which is equal to C minus K transpose Wn inverse plus Cn, the whole thing, inverse times K. And at this point, we are really leading towards the final goal of achieving the Gaussian process for classification, because we have managed to express the posterior of an given Tn, which is now represented as the normal distribution with this mean and this variance. And then we also already know since the beginning what is the probability of Tn plus 1 given an plus 1, which is just a sigmoid. And now we know that integrating this in order to obtain the predictive distribution of this probability distribution, this probability distribution will be a task which is analytically not tractable, but however we can use this approximation where we know that the sigmoid can be approximated by the inverse probit, and then the multiplied with the normal distribution that is actually analytically integrable, and we choose such a probit function which is very close with its parameters to the sigmoid, and then therefore we can actually approximate this integral with a sigmoid function where we have here the sigmoid a and a of with the parameter mu for mean and sigma squared for variance. So then this sigmoid is equal to this term in the argument where the mean mu is in the numerator, and then in the numerator and in the denominator we have the square root of 1 plus pi sigma squared divided by 8, and we simply can use this in our calculation of the predictive distribution as well. So therefore this term will be equal to, I just copied this term here, and now I will just replace, instead of the mu and the sigma squared, the corresponding values from this distribution here, which we can see is this is the mean, and here we have our variance, which is then coupled with the rest of the terms of this informing the argument for the sigmoid function. So, and this is in fact the result. The Gaussian process for classification will result in the sigmoid, which is then having an argument, these terms which are coming either from the kernel, or having some association with the sigmoid function, or belonging to the training set. So we in fact know all these terms here and can simply calculate the term, what is this ratio term here equal to, and from that we perform the sigmoid function, and that is giving us this predictive probability distribution. After we have obtained the Gaussian process for classification predictive distribution, we will also look into how can we learn the hyperparameters and align them with our data. And we will do it in the same way as we did for the regression, where we will be performing the maximization of the model evidence, or the marginal likelihood. The marginal likelihood, Ptn given theta, is given by this integral, where we are having the likelihood function and a prior, which contains the parameters theta in the end. So we are integrating out this an from this equation and obtaining this marginal likelihood this way. And how can we obtain the logarithm of this probability distribution of the marginal likelihood for the purposes of maximizing this marginal likelihood by maximum likelihood estimation? We can do it in a similar way as we did before, where we were modeling the model evidence through a Laplace approximation. And so here is the model evidence modeled by the Laplace approximation. Once again, we had it back in classification as well, and that is equal to, so this C is the model evidence, is equal to the f at z0, and then times the 2 pi powered by n half, and divided by the determinant of a square root of it. So if we perform a logarithm of this, so there will be a logarithm of this function plus this function minus logarithm of this function minus logarithm of this function. And we can see that we have something like that obtained here, where our psi an star now is equal to the ln an star given tn as before, and that is equal to the ln pan given theta plus the ln ptn given an star. So this conditional probability here is given by the multiplication of these two probabilities, or we can say this is a posterior and this is a prior, and the likelihood as we had before. So and we perform now the logarithm, which is this psi function which we defined before, and that it will be serving as our f0. So that will be the value at the mode of this log of this Gaussian, and then we will have minus ln and determinant of this Hessian matrix, which is this term, and then plus and half ln 2 pi, which is this term here. We also see that this term, this Hessian, has the value of Cn inverse plus Wn, as we have seen in the slides before. And then now that we have this log marginal likelihood expressed, we will perform the differentiation so that we can obtain the updates for the gradients for always a new theta while optimizing the theta. And for that, we will have to differentiate with respect to the parameters theta, and but we obtain two sets of terms. First, arising from the dependence on the covariance matrix of Cn on theta, because there are the kernel functions which contain these hyperparameters, and then the rest is arising from the dependence of the vector an of the activations on the theta. We can understand that as A is dependent on the matrix Cn, for example, there will be also therefore this dependence of the an terms on theta. So this will be a slightly lengthy way of devising this derivative, and we will need to do it step by step. So we would like to calculate the derivative with respect to particular hyperparameter theta I of our log marginal likelihood, so that we can use it in our to build the gradient for our iterative gradient-based optimization, like the gradient descent or gradient ascent, perhaps in this example. So, and this problem can be decomposed into solving three derivatives of three different terms. The first term will be the derivative with respect to the hyperparameter theta I of the probability of an star given given theta, so which is the normal distribution of an star with zero mean and with the Cn as its covariance matrix. And then we will have the other term which we will need to solve, the partial derivative of which is the ln of the probability of Tn given an, so this star, so this conditional probability, and then we will have one more term which is, so this is coming from the psi, and this will be the term which is coming from the Hessian matrix, the second order derivative of the psi, in fact, so which results into the so the determinant of this Hessian matrix is Cn inverse plus Wn, and we will need to calculate the partial derivative with respect to the hyperparameters, because these two terms also are including these hyperparameters. So let's start with the first partial derivative with respect to the hyperparameter theta I of the ln of the probability distribution of an star, which contains these hyperparameters. So that is equal to the partial derivative of this entire term here, which is we took out the -1/2, and we have here just a square term from the exponent, and then so we can recognize that this has been taken out from the exponential function of our normal distribution, where we have the n star being the random variable, and the mean would be 0, and the Cn would be the covariance matrix or the precision matrix if it is inverted. And then we will have also this ln Cn determinant. So this was previously in the denominator, but through this negative value here, we have this. We have it in the as a ln of, not in the denominator, but just the term Cn here. And we have already seen, if we perform the derivative of this term with respect to where the Cn is, we derive with respect to the Cn, that was in fact already shown, for example, when we were in the case of regression, where we instead had, instead of an, we had the tn, and that resulted into this term, which is 1/2 an star t transpose Cn inverse. Then we had this partial derivative of Cn with respect to our hyperparameter. So that will need to be specified depending on what type of hyperparameter that is. And then we have the Cn inverse an star. So that is the derivative of this term of when we consider that the Cn inverse is containing the hyperparameter. But we have here a multiplication with an, and this deriving if the an is containing the hyperparameter, which it does, is also needed to be derived, and the result here will be that it is minus Cn inverse an star, and that is so no longer 1/2, and times partial derivative of an star with respect to the hyperparameter. So this was derived like a multiplication, where we first derived with respect to this term and then with respect to the an, and then we have the last term, which is the derivation of this logarithm of the determinant of the matrix, and we have already seen that this is equal to 1/2 trace of the Cn inverse and the partial derivative of Cn with respect to the hyperparameter. So we have expressed this, and we have solved basically this problem. And next, we will look into the partial derivative with respect to the hyperparameter of this likelihood function, and that is we also had the expression of this function before, which is the Tn transpose times an minus this sum. And we can also see that if we perform partial derivative with respect to an of this term, then this is equal to the t, and then this term, as we have seen before, will become this vector of sigma n. So in each component will be the sigmoid function of corresponding an star. Now we have this formulation, this derivative, but this needs to be still multiplied because we performed the derivative only with respect to an, but this needs to be also further derived by the partial derivative of an star with respect to the hyperparameter. So we can at this point sum up what is the derivative of the hyperparameter with respect to the hyperparameter theta I for these first two components, and that is simply, as we had it before, the 1/2 an star transpose Cn inverse exactly as we have it here, and then this, so the whole formula is rewritten here, and then it's added this term, which is the partial derivative with respect to the hyperparameter from the likelihood function, and that is here. And we can observe that this term and this term are these partial derivatives are appearing in both terms, so we can associate this term minus Cn inverse An star with the term Tn minus sigma n, which leads to an which is expressed here. So if we sum up these two terms, we will end up in minus Cn inverse An star plus Tn minus sigma n, and times this partial derivative. However, we know that at the mode, this is this is in fact equal to the partial derivative to the gradient of our the psi function, and this gradient was we realized that is equal to 0, and therefore because we are on the mode, and therefore this whole term is 0, and therefore this term is 0, and that simplifies our formulation for the first two terms, that our partial derivative is this one term plus this trace, or minus 1/2 of the trace Cn inverse a partial derivative of Cn with respect to the hyperparameter. As the next, we will look into the what is the this partial derivative equal to before we put it all together into one expression for the gradient. So now we will describe how do we perform the partial derivative with respect to the hyperparameters of the logarithm of our determinant of the Hessian matrix. We already did a partial derivatives of the matrix or the determinant of a matrix before, so this will be very analogous. First, the first part of the derivation is the outer derivation of the chain rule, so that will lead to the derivation of the logarithm, which will mean then the result is 1 divided by the argument in the logarithm. So, and that leads to the value here of the matrix inverse, because this inverse means that it is in the denominator. So this is the result for the outer part of the logarithm, and the inner part is of integrating this part itself. However, we are using the trace operator for this purpose, as we used exactly before. And here we have this partial derivative of the inverse of the Cn matrix and the partial derivative of this Wn matrix. The Cn matrix, again, of course, needs to be derived with respect to hyperparameters or Cn inverse, because it does contain them. And actually, the Wn is a matrix which contains the sigmoid derivatives and in the diagonal, and those have as an argument An, and the An is also depending on the Cn, and therefore it is also needs to be derived with respect to the hyperparameters. It's not a constant. So if we continue here, we can see that we can split this trace into two one related to this Cn inverse and the rest of the terms, and one with respect to the Wn and these terms. So the first term here is the term where we have this inverse matrix multiplied with the partial derivative of Cn inverse with respect to the hyperparameter. And we know from the previous slides that this is equal to the Cn inverse times the partial derivative of Cn with respect to the hyperparameters times Cn inverse. So that part is already solved, except one more detail, that here the partial derivative will have here a negative sign, and we move this negative sign here. So that's why here is minus in front of the trace. And the second part is simply the inverse of the matrix times the partial derivative of the matrix Wn with respect to the hyperparameter. There are a few changes in the notation so that there we have some similar formulations as is in the book. It turns out that this Cn inverse plus Wn, the whole inverse, can be rewritten as 1 plus Cn Wn inverse. And we can see here how this comes to place. So in fact, so this whole term with this Cn inverse here, the inverse of the matrix times the Cn inverse is equal to this term in the bracket, and we can see that if we multiply this term from the trace with the inverse of the matrix 1 plus Cn Wn inverse, so without the inverse, we end up in identity. Why do we end up in identity? Well, let's simply multiply the I with the Cn inverse and the Cnwn with the Cn inverse, and we will end up in Cn inverse plus Wn, and that's exactly the same as here, except that it's not inverse, so these two will cancel each other out in order to have identity. That leads to the fact that this term here is inverse to this term here, and that also means that Cn inverse plus Wn whole thing inverse times Cn inverse is equal to 1 plus Cn Wn inverse. So here, therefore, we can place, instead of the Cn inverse plus Wn inverse Cn inverse, we can place this term instead. And in the second part here, we are having this one integral, which we will deal with it a little bit later. And we have this formula instead of the original formula, so that these two expressions are similar, except that here we have part of the definition of this term is also the Cn inverse, and therefore we need to add one Cn here because the Cn inverse was not here before. So with that, we have a new formulation. For these partial derivatives, we can just put in the partial derivative with respect to a particular hyperparameter, and we were dealing with this already before in the case of the regression. So we have the partial derivative with respect to some variance or some scaling parameters well defined already, and that could be put then in this instead of this term. For this term, we will devise it further in the next step. So far, coming back to our partial derivative of our marginal likelihood, is that it is equal to the first term, which is associated originally with the exponent of the normal distribution, and then this term is associated with the ln determinant Cn, and then we have these further two terms where one is associated with these terms, and the other term is associated with the trace part, which is associated with the Wn derivatives. So now in the next step, we will see how we can put these two together, how we can express these two together, and then finally we'll express the part where the Wn is present. How we can put together the trace terms which are associated with the Ln of some determinant of a matrix. So the first term here, we can see that in the trace it has Cn inverse times the partial derivative. The second one has Cn inverse times an inverse matrix times the derivative, and therefore we can put them together into one trace and take out the Cn inverse in front, the term, and then this Cn inverse is multiplying the identity plus Cn Wn inverse minus identity matrix. This identity comes from here. So here we have minus, and this Cn is associated with identity instead of this term here. So, and what can we do further with this? Can we further somehow reformulate it? And we can imagine that we have this term, and instead of identity, we put there this matrix and its inverse. So it will be, for the identity, it will be I plus Cn Wn inverse times I plus Cn Wn. And in such a case, we can put them together, and we will have like I plus Cn Wn inverse, and then we will have identity minus I plus Cn Wn. And now if we take away the brackets, we will see that the I minus I cancels itself out, and we will be left out only with the Cn Wn terms, which means that this formulation of the matrix can be reformulated into formulation with a multiplication instead. So here we will have therefore minus I plus Cn Wn inverse times Cn times Wn. So therefore we can formulate our gradient, now updated, that we have only one trace less here, and we have here the formulation for the both two traces in one term. And finally, we have the trace associated with the partial derivative of Wn with respect to the hyperparameters, and let's have a look how that can be formulated. What remains is to perform the derivative, this partial derivative of the matrix Wn with respect to the hyperparameters. And it needs to be noted that this matrix contains the sigmoid times 1 minus sigmoid terms along the diagonal, and this sigmoid has as an argument the ANs activation, and those are dependent on the hyperparameters. Therefore, we can use the chain rule for calculating this overall gradient, and therefore first we derive the Wn with respect to An, and then we will perform the partial derivative of the An with respect to the particular hyperparameter. So let's get to it, and we can see that we can solve this task by independently performing these derivatives and multiplying them together. So if we look at the derivative of the Wn with respect to An, we can see that this is the definition of our terms on the diagonal. Because this Kronecker delta will give us values which are only 1 if the n is equal to m, and therefore these are the terms on the diagonal, and we need to perform the derivative of it. Here is the outcome of after the derivation, and we can see that here we have one more term, which is 1 minus 2 sigmoid an as a result of this derivative. Now, let's see how we got to it. First, we can see that we have the product of the sigmoid times 1 minus sigmoid, and that we can therefore derive as with the product rule. If we first have this sigmoid to be underived, and the second one is derived, therefore here we first will have like a minus 1 from the derivative, because here is the negative value, so we can put this sigmoid an and this minus from here times the derivative associated with this term here, which results into the sigmoid an times 1 minus sigmoid an. That is because once we took out this minus here, the derivative of this function is just sigmoid an, which is equal to exactly to this term. And then the second part is if this first term we derive, so then it is sigmoid an times 1 minus sigmoid an, and this second term is underived, so it stays 1 minus sigmoid an. So this is the term, and now if we put things together, we will realize that we can take sigmoid an times 1 minus sigmoid an in front of the other terms, as we have it here, and then we will end up with minus sigmoid an plus 1 minus sigmoid an, and this leads to the new term 1 minus 2 sigmoid an. So we have performed the derivative here of this first part, and now we need to perform the derivative of the second part. Now, for the an, we know that an star is the an corresponding to the maximum a posteriori estimation, so it is the mode of this approximated distribution, and therefore, actually prior distribution, and therefore it is also equal to this term. And this term Cn dn minus sigmoid n, which we have devised earlier, will lead us to the fact what is how should we find the derivative of an with respect to the hyperparameter. So in this case, we can see that here we can again, or have to again deal with it as a product of two parts which both can be have a derivative with respect to the hyperparameter. So first we derive with respect to the Cn, and that is the Cn with respect to derivative of Cn with respect to the hyperparameter, the term which we will always be able then to replace by the particular form of this derivative as before, and then the second part is underived plus the first is underived, and then we are performing the derivative of the sigmoid n because it contains the an's in the argument, and therefore we will see that what is this derivative equal to. So again, we have the same. The first is the same, and here the derivative of the sigmoid is in fact generating us the Wn matrix. So we have here therefore, and it's minus here, therefore we will have here minus Cnwn, and then an with respect to the theta I hyperparameter. This now, if we observe it, can be put into under one formula where we will have the following terms. As a result of our derivative, we ended up with having the partial derivative of an with respect to the hyperparameter both on the right side and also on the left side. Therefore, if we move this part to the other side, we will have the term this partial derivative which will be multiplied by I plus Cn Wn, because the I, the identity matrix comes from this term, and the plus Cn Wn comes from this term. So this is on the left hand side here, and then we can divide by this the inverse of that matrix, and we will end up on the right hand side having, so this term will vanish, and this term will be multiplied with the inverse of that matrix which was on the left hand side. So it will be suddenly I plus Cnwn inverse times the Cn with respect to derivative with respect to the hyperparameter Tn minus sigmoid n vector. And this is basically the outcome of this derivative. We can see that the trace term which we had previously, which we were trying to solve what is its content. So this is the last part which we were solving. The what is it equal to is equal to. So these were the components in the trace already before, and we simply add these terms, which is a product of these two terms. So where one is this term here, another diagonal matrix, and the other one is this term here, which is expressing, or again, a partial derivative of Cn with respect to the hyperparameter. And that's why this term is now concatenated with the partial derivative of Wn with respect to An, and the partial derivative of An with respect to the hyperparameter theta. And now we have the trace fully expressed, and we can put it into the rest of our marginal likelihood derivative, and that is now equal to the all the components which we have devised. So the first component, which is representing the originating from the exponential terms. Then we have these terms which are associated with the ln of the matrix, and then we have the term which is associated also with the ln of the matrix, but specifically of this Wn with respect to the hyperparameter derivative, which is this very long trace. And with this we have completed our search for the gradient, and we would be able to put this rather complicated formula, but otherwise with all entries well known, into the gradient descent, or in this case gradient ascent computation, as we are trying to maximize this likelihood, marginal likelihood function, so that, and we are in that we are searching for the hyperparameters which would be maximizing this function. So with that, we have completed our discussion on Gaussian processes in terms of Gaussian processes for regression, classification, and we have also discussed how we can further learn not only the kernel and the predictive distribution, but also how we can learn the hyperparameters so that we are maximizing the predictive power of our kernel machine learning framework. Finally, we can see one example of the classification using the Gaussian process for classification framework, where we have a two-class problem with our training set. We can see the training data is either circles or the red crosses, and we can see in the green the true distribution of the true boundary of these two classes. And now we can see the other boundary here in black, and this is actually our posterior probability, which is approximated by the Laplace approximation, and that one is showing us this value of probability equals 0.5. So this is the decision boundary, and it is calculated like if we would be calculating now for each point in space, what is the, for this point, input point, two-dimensional input point, what is the probability, we will simply have it in our predictive Gaussian processes based framework. It will give us, this point will be the x capital N plus 1, and will be simply the part of the predictive probability distribution of Ptn plus 1 given Tn and Xn and this point x capital N plus 1, and we will get as an outcome some value of this posterior probability, and that will be something between 0 and 1. So these values will be rather, let's say, large because it will be close to 1 if the circles will be the class 1, and then these values will be something close to 0, and values around the decision boundary will be something which is close to 0.5. So this is simply the plot for each pixel within this canvas. We have evaluated what is the posterior probability between 0 and 1, and gave it a color between blue and red. Finally, we shortly restate what has been shortly discussed before in the case of the linear models for regression and classification, and that is that the Gaussian process feature that is different to these models which are parameter based is that the Gaussian process as the next neural network with a regularized infinite feature space. So the kernels can be defined such that they would be corresponding to a sum of infinitely many features. And that is the, in some sense, this flexibility is advantage of the Gaussian process, and the cost of the Gaussian process would be that overall the number of training points is much larger than the amount of features we are dealing with in machine learning, and we will need to actually have our algorithms n-bound, not m-bound, and for example, for the inversion of a matrix, we will typically need to have O(n) cubed complexity compared to O(m) cubed when we are dealing with limited finite features. But our prediction with Gaussian processes can be seen as an identical special case of Bayesian neural networks with a prior on weight vector, which will have an increasing number of features in the hidden layer, very large one, up to an infinite amount of features. It will, in that limit, it will become a Gaussian process. It will tend to become a Gaussian process with the increasing number of features in the hidden layer of a two-layer network. And then also one needs to note the difference that in neural networks, the hidden layer units are shared among the output layer units as they are trained and jointly, and they get the output layer can borrow statistical strength from various hidden layer units. So, and this sharing of hidden layer units is not present in Gaussian process. So we can say that this in infinity, this property is lost in the Gaussian process limit. With this, we have completed the chapter 6 on kernel methods of the textbook Pattern Recognition and Machine Learning by Christopher Bishop, and I will see you on the next chapter on sparse kernel machines.